Hello, wonderful souls. Welcome back to Sleepy Science, where we explore the universe's greatest mysteries with gentle curiosity and wonder. Tonight, we're witnessing something extraordinary, a visitor from another star system passing through our cosmic neighborhood at this very moment. December 19th, 2025. Mark this date in your mind. On this day, humanity will experience something that happens perhaps once in a generation, an interstellar comet, a traveler from another solar system, billions of miles away, will make its closest approach to Earth. But here's what makes this particular visitor so captivating. It's changing faster than anyone predicted. It's behaving in ways that challenge what we thought we knew about objects from beyond our solar system. Scientists are watching in real time as 3IATLAS defies expectations, brightening unexpectedly, releasing gases at impossible distances, and revealing chemistry that shouldn't exist according to our models. What secrets is this ancient wanderer carrying? What can it tell us about worlds we'll never see? If you're ready to embark on this cosmic journey with me to unravel the mystery of this accelerating visitor from the stars, I'd love to have you along for the adventure. A quick tap of that like button lets me know you're here. And subscribing means you'll never miss these celestial stories. And hey, if you're listening as you drift towards sleep, that's exactly what this channel is for: learning while you rest, exploring while you dream. Let me paint you a picture of where we are in this moment. Right now, as you listen to these words, there's an object moving through space at 137,000 miles per hour. That's roughly 200 times faster than a bullet. It's not from here. It didn't form around. Our sun wasn't born in our neighborhood of the cosmos. This visitor, officially designated 3IATLAS, came from another star system, entirely carrying with it the frozen chemistry of a world we'll never visit, shaped by a sun we'll never see. Think about that for a moment. In your lifetime, in my lifetime, we're witnessing only the third confirmed interstellar object ever detected passing through our solar system. The first was Oumuamua in 2017, that strange, elongated visitor that appeared and vanished before we could truly study it, leaving behind more questions than answers. The second was 2I Borisov in 2019, a more conventional comet that behaved mostly as expected, though it too carried the chemical signature of another stellar system. But 3IATLAS. This one is different. This one is rewriting the playbook. When astronomers first calculated its trajectory in early July 2025, they expected a certain level of activity based on distance from the sun, based on size estimates, based on what they'd learned from Borisov. They were wrong, spectacularly wrong. The comet began displaying active cometary behavior, releasing gas and dust, forming a visible coma when it was still 6.4 astronomical units from the sun. For context, that's roughly 600 million miles away, well beyond Jupiter's orbit. At that distance, the sun's warmth should barely touch it. Water ice doesn't sublimate at such distances. Yet, 3IATLAS was already alive, already changing, already defying the rules. As it drew closer to the sun through the summer and fall of 2025, the surprises continued. Observations from the James Webb Space Telescope revealed something unprecedented: a carbon dioxide to water vapor ratio of roughly 8:1. Let me emphasize this. That's the highest ratio ever recorded in any comet solar system or otherwise. It's 16 times greater than what we expected at the comet's distance from the sun. This isn't just unusual, this is profound. This tells us that 3IATLAS formed in conditions radically different from anything in our solar system, in a region of its parent star system, where carbon dioxide ice dominated over water ice. What kind of planetary system produces such chemistry? What kind of stellar nebula? What kind of protoplanetary disk? What combination of temperature, pressure, and elemental abundance creates a world where CO2 reigns supreme? These are questions we're only beginning to ask. Then came the brightness surge. In late September, just before 3IATLAS passed behind the sun, as viewed from Earth, Citizen scientists using the Interstellar Network, a global community of amateur astronomers with modest telescopes, detected an unexpected spike in the comet's brightness. It wasn't gradual, it wasn't predicted. The comet was suddenly releasing more material, more energy, becoming more active than any model suggested it should be. When NASA's Stereo spacecraft and the joint ESA-NASA SOHO observatory tracked it through October as it rounded the sun, they confirmed what the citizen scientists had seen. 3IATLAS was in the midst of what appeared to be an outburst, a sudden increase in volatile release that exceeded all expectations. This brings us to perhaps the most intriguing question: why? Why is this comet so active? Why does it behave so differently from 2I Borisov, which was relatively well behaved? Why does it differ so dramatically from the comets born in our own solar system? One possibility lies in its age. Current estimates suggest 3IATLAS could be between 7 and 14 billion years old. Let that settle in your mind for a moment. 7 to 14 billion years. Our entire solar system is 4.6 billion years old. This means 3IATLAS might have formed when the universe was less than half its current age, when the Milky Way was still taking shape, when the very elements that make up your body were still being forged in ancient stars. It's older than our sun. It's older than Earth. It's older than the planets, the asteroids, every comet we've ever studied. It's a fossil from the early universe preserved in the deep freeze of interstellar space. For billions of years, this object has been traveling through the void between stars bombarded by cosmic radiation, its surface altered by the relentless solar wind from whatever star it once orbited. The ices within it, the carbon dioxide, the carbon monoxide, the water, the organic compounds have been slowly modified by this radiation. Cosmic rays break apart, molecules rearrange chemical bonds, create exotic forms of ice that we can't easily replicate in laboratories. When 3IATLAS entered our solar system and began warming up, these exotic ices started sublimating, transforming directly from solid to gas. And perhaps they do so more violently, more energetically than the pristine ices of solar system comets. There's another factor to consider: its origin. Analysis of 3IATLAS's trajectory and velocity suggests it came from either the Milky Way's thin disk or thick disk population. The thick disk is composed of older stars, stars with lower concentrations of heavy elements than our sun's stars that formed earlier in galactic history. If 3IATLAS was ejected from a planetary system orbiting a thick disk star, it would have formed from primordial material with a different elemental composition than our solar system. Different ratios of carbon to oxygen, different abundances of nitrogen-sulfur metals. These compositional differences would be locked into the comet's ices and dust, creating chemistry we've never encountered before. Consider the implications. Every solar system is unique. Every star has its own blend of elements, its own temperature structure. In the protoplanetary disk, its own dance of forming planets that gravitationally sculpt the orbits of smaller bodies. In our system, Jupiter was the great ejector, flinging countless comets out into interstellar space through gravitational encounters. Somewhere in another star system, light years away, another Jupiter, another massive planet, did the same thing to 3IATLAS billions of years ago. That planet is still out there orbiting a star we might never identify. And the comet it threw out has traveled across unimaginable distances to arrive here now, in December of 2025. Have you ever thought about the journey? The sheer improbability of this encounter space is almost incomprehensibly empty. The average distance between stars in our galactic neighborhood is about 4 to 5 light years. That's roughly 25 trillion miles. 3IATLAS has been traveling through this emptiness for millions of years, perhaps billions, moving at about 35 miles per second, relative to nearby stars when it was in interstellar space. At that speed, it takes roughly 20,000 years to travel a single light year. The odds of an interstellar object randomly encountering another star system are vanishingly small. Yet, here it is. Here we are, watching it, studying it, learning from it. And it's changing as we watch. The dust mass loss rate, the amount of material streaming off its surface every second, varies between 0.3 and 4.2 kilograms per second depending on its activity level. That might not sound like much, but over days and weeks it adds up. The comet is literally losing mass-shedding layers of ancient ice and dust that have been locked away since before our world existed. Each grain of dust released into space carries information. Each molecule of gas provides a clue. The nickel-to-iron ratio in the gas released by 3IATLAS is unusually high compared to solar system comets. What does that tell us about the star it once orbited? About the supernova explosions that enriched its birth? Nebula with heavy elements. As December 19th approaches 3I, Atlas will be approximately 1.8 astronomical units from Earth, about 170 million miles. In cosmic terms, this is remarkably close. It's closer than Mars is at its most distant. Yet it's also perfectly safe. There's no danger, no risk, no cause for concern. The comet's trajectory is well understood, tracked by dozens of observatories worldwide and spacecraft throughout the solar system. It will pass on the opposite side of the Sun, from Earth continuing its journey, outward accelerating as it moves away from our star's gravitational embrace. But here's what makes December 19th special. It's the closest we'll ever be to this particular messenger from another world. After that date, 3IATLAS will continue outward passing Jupiter's orbit in March 2026, and then silence. It will fade from our telescopes, become too faint to study, too distant to track. Eventually, it will leave our solar system entirely, returning to the interstellar void from which it came. We will never see it again. No human will ever have another chance to study this particular object. This is our moment, our brief window, our singular opportunity to learn what we can from a traveler that has seen things we cannot imagine. Think about what this comet has witnessed in its lifetime. If it truly is 10 billion years old, it existed when the Milky Way looked different than it does today, when the spiral arms were shaped differently, when entire generations of stars were born, lived, and died. It may have passed close to dying stars, witnessed supernovae from a relatively close distance, survived the gravitational chaos of its home system being disrupted by a passing stellar neighbor. Every scar on its surface, every layer of ice, every embedded grain of interstellar dust is a page in a history book we're only now learning to read. And it's changing faster than expected. That phrase keeps echoing in the observations, in the scientific papers, in the surprise comments from researchers. Faster than expected, more active than predicted, behavior inconsistent with models. These are the kinds of statements that make scientists excited because they signal something new, something we don't yet understand. They signal the opportunity to expand our knowledge, to question our assumptions, to build better models of how the universe works. So, what happens on December 19th? In one sense, nothing dramatic. The comet will reach its closest point to Earth, still millions of miles away, visible only through moderately powerful telescopes to dedicated observers. There will be no spectacular sky show, no visible display for the naked eye, no comet tail stretching across the heavens. In another sense, everything happens on December 19th. On that date, humanity will have its best opportunity to study an object from another star system. Telescopes around the world and spacecraft throughout the solar system will be trained on this visitor. Data will pour in: spectra images, measurements of gas production, rates, observations of the coma structure, tracking of the dust trail. Every piece of data is precious. Every observation adds another brushstroke to our portrait of 3IATLAS, and by extension to our understanding of planetary systems beyond our own. This isn't just about one comet. This is about beginning to understand the diversity of the cosmos. Our solar system is just one example of how star systems can be structured, how planets can form, how chemistry can evolve. For centuries, it was the only example we had. Now, finally, the universe is delivering samples to our doorstep. Oumuamua showed us that interstellar objects can be strange, perhaps asteroid-like, certainly mysterious. 2I Borisov showed us that some interstellar comets might be similar to our own. And now, 3IATLAS is showing us something different again. Extreme chemistry, unexpected activity, ancient ice behaving in ways we've never seen before. Each interstellar visitor is weird in a different way. Each one expands our understanding. Each one challenges our assumptions. This is how science progresses, not through confirming what we already believe, but through encountering phenomena that don't fit that demand explanation, that force us to think more deeply about how nature works. As we stand on the edge of this close encounter as December 19th approaches, there's something profound about the moment. We're living in the first generation of humans who can study these interstellar travelers in detail. Our ancestors looked at comets with wonder and fear, weaving them into myths and omens. Our great-grandparents began to understand comets as icy bodies from the outer solar system. Our grandparents watched as spacecraft visited comets for the first time. And now, we're watching objects from other star systems pass through our neighborhood, carrying messages from distant suns. What will the next generation study? How many more interstellar visitors will they catalog? What will they learn that we can only dream of? The story of 3IATLAS is still being written. The data from December 19th hasn't been collected yet. The analysis will continue for years. But already this comet has taught us humility. It has shown us that the universe is more diverse, more strange, more wonderful than our models predicted. It has reminded us that out there beyond our small corner of space, there are countless worlds with their own histories, their own chemistries, their own stories to tell. And occasionally, very rarely, one of those worlds sends us a messenger. But to truly understand why 3IATLAS is so special, we need to go back to the beginning. We need to understand how it was found in the first place. How do you spot a single faint object moving through the densest star fields in the sky? How do you distinguish one moving point of light from billions of stationary ones? How do you realize within days that what you're looking at came from beyond our solar system? The discovery story of 3IATLAS is itself a testament to human ingenuity, technological advancement, and the persistent curiosity that drives us to watch the skies. And that story begins on a night in early July 2025 when a robotic telescope in Chile captured something unexpected. The night of July 1st, 2025 was like any other at the Atlas facility in Rio Hurtado, Chile. The robotic telescope, one of 4 in a global network designed to scan the skies for potentially hazardous asteroids, was doing what it does every clear night, capturing wide-field images of the heavens, comparing them to previous observations, searching for anything that moved. The system is automated tireless, capturing thousands of images each night, processing them through algorithms designed to flag unusual motion. On this particular night, the algorithm detected something at coordinates that placed it near the border of the constellations Serpens Quota and Sagittarius, moving against the background stars. At magnitude 18, roughly 4,000 times fainter than what the human eye can see, this object was unremarkable to the automated system. Just another entry in the database flagged for human review. But when Atlas team member Larry Deneau examined the detection later that day, something about the trajectory seemed wrong. The object was moving too fast at an unusual angle. It was 4.51 astronomical units from the Sun, approximately 420 million miles away, and traveling at 61 kilometers per second. That's 136,000 miles per hour. Something about those numbers didn't add up. Here's what makes this discovery so extraordinary. The object was positioned directly in front of the Milky Way's galactic center, the densest concentration of stars visible from Earth. Imagine trying to spot a single firefly against the backdrop of 1,000 bonfires. That's essentially what ATLAS accomplished. The galactic center region is so crowded with stars that automated detection systems often struggle to distinguish real moving objects from the noise of stellar backgrounds, slight variations in brightness, and instrumental artifacts. Amateur astronomer Sam Dean later analyzed the circumstances and noted that 3IATLAS had likely been visible for weeks before its official discovery, but was simply too difficult to detect against that stellar backdrop. If it had been moving through a less crowded region of the sky, we might have found it weeks earlier, giving us even more time to prepare observation campaigns. Within hours of Deno's initial review, he reported the object to the Minor Planet Center, the internationally recognized clearinghouse for observations of asteroids, comets, and other small bodies. The designation assigned was temporary A11PL3Z. The report included the object's position, its apparent motion, and a preliminary estimate of brightness. What it couldn't yet tell was the most important question: where did this object come from? This is where the global astronomical community shows its strength. Within a day, observatories around the world began turning their telescopes toward those coordinates. Professional astronomers and dedicated amateurs alike recognized that this fast-moving object warranted immediate attention. The Zwicky Transient Facility at Palomar Observatory in California, a survey system designed to find transient astronomical events, searched its archives. There, in images captured on June 28th and 29th, was the object already cataloged, but not yet identified as unusual. Further searches revealed even earlier detections, June 14th through 21st. Pre-discovery observations are gold in astronomy because they extend the observational arc, allowing for much more precise orbit calculations. Suddenly, instead of having mere hours of observational data, astronomers had nearly 3 weeks. But there was still a fundamental question: what was this thing, asteroid or comet? On July 2nd, several observatories attempted to answer that question. Alan Hale, yes, the co-discoverer of Comet Hale-Bopp, one of the most spectacular comets of the 20th century, observed the object and reported no obvious cometary features. It appeared point-like, more consistent with an asteroid, but other observers saw something different. The Deep Random Survey Telescope in Chile, the Lowell Discovery Telescope in Arizona, and the Canada-France-Hawaii Telescope atop Mauna Kea all captured images showing a marginal coma, a slight fuzziness surrounding the central point, and a potential tail-like elongation extending about 3 arcseconds. 3 arcseconds is tiny, roughly equivalent to the apparent size of a penny viewed from a mile away, but it was there. The object was active. It was releasing gas and dust. It was a comet. This distinction matters more than you might think. Asteroids are rocky or metallic bodies, essentially inert chunks of material that don't change much as they orbit the sun. Comets, by contrast, are icy bodies that wake up as they approach the sun, sublimating their volatile ices and creating spectacular displays of gas and dust. The fact that 3IATLAS showed cometary activity while still so far from the sun, 4.5 astronomical units well beyond Mars, was the first hint that this was no ordinary comet. Legendary planetary scientists David Jewett and Jane Liu, the duo who discovered the first Kuiper Belt object beyond Neptune in 1992, fundamentally changing our understanding of the outer solar system, observed 3IATLAS using the Nordic Optical Telescope on July 2nd. Their report was unambiguous, clearly active, with a diffuse appearance. When Jewett and Liu call something interesting, the astronomical community listens. These are scientists with decades of experience studying the faint, distant, and unusual. Their confirmation that 3IATLAS was genuinely active lent credibility to the idea that this might be something special. But the most crucial question remained: where was it going? Or more precisely, where had it come from? Calculating an orbit requires mathematics that would have astounded our ancestors. Newton's laws of motion and universal gravitation provide the foundation. But the reality is far more complex. You must account for the gravitational influence not just of the Sun, but of Jupiter, Saturn, and the other planets. You must consider the forces generated by the comet's own outgassing. Those jets of gas and dust create tiny but measurable changes in trajectory, like a miniature rocket engine firing at random intervals. You must factor in observational uncertainties, the slight errors inherent in measuring position from Earth-based telescopes peering through our turbulent atmosphere. As observations accumulated through early July, orbital dynamicists, specialists in calculating celestial mechanics, began running the numbers. They worked backward, tracing where the object had been weeks, months, years before. Standard orbit-fitting programs assume elliptical orbits, the kind that bind comets and asteroids to the Sun in closed loops. But for 3IATLAS, these programs kept returning something else, a hyperbolic orbit. The eccentricity, a measure of how elongated an orbit is, came out to approximately 6.1. An eccentricity of 0 describes a perfect circle. An eccentricity of 1 describes a parabola, the borderline case where an object has just barely enough energy to escape the Sun's gravity. Anything greater than 1 describes a hyperbola, an open trajectory, unbound, never returning. An eccentricity of 6.1 is unequivocally hyperbolic. This object was just passing through. More telling still was the velocity at infinity, the speed the object would have relative to the Sun if it were infinitely far away beyond the Sun's gravitational influence. This value came out to approximately 57 kilometers per second. To put that in perspective, Earth orbits the Sun at about 30 kilometers per second. Objects bound to the Sun, no matter how elliptical their orbits, will always slow down as they climb away from perihelion, eventually falling back. But objects with hyperbolic orbits never slow down enough to fall back. They escape. The velocity at infinity tells us how fast they're moving through the galaxy, independent of the Sun's gravity. At 57 kilometers per second, 3IATLAS is moving faster relative to the Sun than any solar system object could naturally achieve. On July 2, 2025, just one day after the initial Atlas detection, the Minor Planet Center made it official. They assigned the interstellar designation 3I, signifying that this was the third confirmed interstellar object ever detected. They also gave it a more traditional cometary designation, C 2025 N1 Atlas. The C indicates a non-periodic comet, one that's not expected to return. The 2025 N1 tells us it was the first such comet discovered in the second half of July 2025. The N designates the date range, and Atlas credits the survey that found it. By this point, 122 observations from 31 different observatories had been reported to the Minor Planet Center. Think about that global effort. Within 48 hours of the initial detection, 36 observatories across 6 continents had contributed data. Some were massive professional facilities with mirrors several meters across. Others were backyard setups operated by dedicated amateur astronomers with telescopes no larger than what you might buy at a decent camera shop. All of them working together, all contributing to our understanding of this visitor from beyond. But here's where the story gets even more interesting. Remember those pre-discovery images? Astronomers began searching archives more systematically. The Zwicky Transient Facility had captured 3IATLAS multiple times in June. Atlas's own global network with telescopes in Hawaii, Chile, and South Africa had imaged it repeatedly without initially recognizing it as significant. Perhaps most remarkably, NASA's TESS, the Transiting Exoplanet Survey Satellite, a space telescope designed to find planets around other stars by detecting tiny dips in stellar brightness, had serendipitously captured 3IATLAS in its wide-field images from May 7th through June 3rd. TESS observations are fascinating because they revealed that 3IATLAS was already bright and active in early May, when it was roughly 6.4 astronomical units from the Sun, about 600 million miles, approximately the distance of Jupiter. At that distance, solar heating is minimal. The intensity of sunlight follows an inverse square law: double the distance and you receive 1/4 the energy. At Jupiter's distance, sunlight is 25 times weaker than at Earth. Water ice simply doesn't sublimate effectively at such distances and such low temperatures. The surface temperature of a comet at 6 AU is perhaps 120 Kelvin, roughly minus 240 degrees Fahrenheit. Water ice remains solid and stable. Yet, 3IATLAS was active. The only explanation is that it contains highly volatile ices compounds that sublimate at much lower temperatures than water. Carbon dioxide sublimes at around 140 Kelvin. Carbon monoxide is even more volatile, subliming at 70 Kelvin. These supervolatiles can drive cometary activity at vast distances from the Sun, creating comas and tails when water ice would remain frozen and inert. The fact that 3IATLAS was already active in May told researchers immediately that this comet had unusual composition, rich in these exotic ices. There's another archive that captured 3IATLAS before its official discovery, the Vera C. Rubin Observatory. This facility, still in its commissioning phase in June 2025, is destined to revolutionize astronomy when it begins full science operations. With an 8.4-meter mirror and the largest digital camera ever built for astronomy, 3.2 billion pixels, the Rubin Observatory will photograph the entire visible sky every few nights, creating a continuously updating movie of the cosmos. During science validation observations from June 21st to July 3rd, the Rubin Observatory happened to image the region containing 3IATLAS. Researchers later analyzed those images and found the comet clearly visible with measurable coma diameter that grew slightly over those 2 weeks. The analysis also helped constrain the size of the nucleus, the solid icy core, at the heart of the coma. Here's a sobering thought: if the Rubin Observatory had begun its science validation observations just 2 weeks earlier, it would have discovered 3IATLAS before Atlas did. Think about the name then, 3I Rubin instead of 3IATLAS. It's a reminder that discovery is often a matter of timing, of looking at the right place at the right moment with the right instrument. Why does any of this detective work matter? Why spend so much effort piecing together these pre-discovery observations, calculating these orbits, confirming and reconfirming the interstellar nature of the object? Because we're building a statistical understanding of how common these visitors are. Before 2017, before Oumuamua, we had theories about interstellar objects, but zero confirmed detections. We didn't know if they passed through the solar system once per century, once per decade, once per year, or multiple times per year. Now, with 3 confirmed detections in 8 years, we're starting to get a handle on the numbers. Current estimates suggest that at any given time, there might be dozens of interstellar objects within Neptune's orbit, most too small or too faint for us to detect with current technology. The Rubin Observatory, when fully operational, is expected to discover dozens to potentially hundreds of interstellar objects over its 10-year survey lifetime. Suddenly, what was once a curiosity will become a population we can study statistically. We'll be able to ask questions like, what percentage are comets versus asteroids? Do they come preferentially from certain directions in the galaxy? What's the typical size distribution? How diverse are their compositions? Each individual discovery is precious, but the real science comes when you have enough examples to see patterns, to test theories, to understand the general principles rather than just cataloging oddities. This brings us to a subtle but important point about the discovery process. Recognizing what you're looking at requires both good data and good intuition. When Atlas detected 3IATLAS, the automated system didn't flag it as interstellar. It simply noted an object with unusual motion. It took human judgment, Larry Deno, recognizing that something about the speed and trajectory seemed off to trigger the follow-up that led to confirmation. Automated surveys are essential for finding these objects in the first place, but human expertise remains crucial for interpreting what those detections mean. Consider the challenges. On any given night, survey telescopes like ATLAS detect thousands of moving objects. The vast majority are known asteroids whose orbits are already well characterized. Some are newly discovered asteroids that turn out to have conventional orbits around the sun. A few are comets, and very, very rarely you get something from beyond. The skill lies in recognizing which detections warrant intensive follow-up, which might be truly unusual, which could be interstellar. Miss that judgment call, and the object might fade before you can gather enough data to determine its nature. This is why the astronomical community reacted so quickly to the announcement. Within hours, telescopes were being repointed. Observations were being scheduled. Spectroscopy, the science of splitting light into its component colors to reveal chemical composition, was being planned. Every clear night was precious because comets are dynamic. They change as they approach the sun. They can fragment, flare, fade. If you want to understand what you're looking at, you need data from as many stages of their evolution as possible. And 3IATLAS was already showing its dynamic nature. Those early observations in June and July revealed a comet that was brightening faster than standard models predicted. Cometary brightness typically follows a power law with distance. As you get closer to the sun, the increased solar heating drives more activity, and the comet gets brighter in a predictable way. But 3IATLAS was exceeding predictions. It was brightening steeply, suggesting either that it was larger than initial estimates, or that it was more active, or that it contained unusual ices that were being preferentially released as it warmed. As it turned out, the answer was unusual ices, but we're getting ahead of ourselves. The discovery phase of 3IATLAS, from initial detection to confirmed interstellar status, took less than 48 hours. That's remarkably fast, a testament to modern observational capabilities and international cooperation. By comparison, Oumuamua's interstellar nature wasn't confirmed for about a week after discovery, and even then, there was significant debate. The combination of better survey technology, more observatories, and the lessons learned from previous interstellar objects allowed for rapid confirmation this time. But rapid confirmation also meant rapid planning. If this object was going to pass through the inner solar system, over the coming months, astronomers needed to coordinate. Which telescopes would observe when? What instruments would be used? Which wavelengths of light would be most informative? How could spacecraft scattered throughout the solar system contribute? The scale of the coordination effort that followed. The discovery is itself a story of modern astronomy, but more on that later. For now, consider what had been accomplished in those first few days of July 2025. A robotic telescope in Chile had spotted a faint point of light moving against the stellar background. Human expertise had recognized that motion as unusual. Global follow-up had confirmed the object's existence and trajectory. Orbital calculations had revealed its interstellar origin. Spectroscopy and imaging had shown it to be an active comet. Archives had been searched, extending the observation record backward by weeks. All of this happened while the comet was still 5 astronomical units from the sun, months before its closest approach, giving astronomers precious time to plan comprehensive observation campaigns. The discovery of 3IATLAS was a victory for systematic sky surveys, for international cooperation, for the marriage of automated detection and human interpretation. It was also a reminder of how much we still have to learn. Even with all our technology, we almost missed this object, because it was passing through a crowded star field. How many others have we missed? How many interstellar visitors have slipped through the inner solar system undetected because they weren't bright enough, weren't in the right part of the sky, or passed through when we weren't looking? These questions matter because they affect our understanding of the universe. Every confirmed interstellar object updates our estimates of how many exist, how they're distributed, what they're made of. Every discovery is a data point. In a larger picture, we're still assembling piece by piece, detection by detection. But discovering 3IATLAS was just the beginning. Confirming it came from interstellar space answered one question and raised a dozen more. What was it made of? How big was it? Why was it so active so far from the sun? The answers to those questions required a different kind of observation, a deeper analysis of the light this ancient traveler was reflecting and emitting. And what those observations revealed would challenge our understanding of cometary chemistry in ways nobody anticipated. When you look at a comet through a telescope, you're seeing light-reflected sunlight, bouncing off dust particles and emissions from gases excited by solar radiation. But hidden within that light is information. Every wavelength, every color, every subtle absorption line tells a story about what that comet is made of, what temperatures it experienced during formation, what kind of star system gave it birth. In August 2025, when the James Webb Space Telescope turned its infrared eyes toward 3IATLAS, the story it revealed was unlike anything we'd seen before. The ratio of carbon dioxide to water vapor was 8-to-1. 8-to-1. Let me say that again because it's so extraordinary. For every molecule of water being released from this comet, 8 molecules of carbon dioxide were escaping into space. This is the highest CO2 to water ratio ever measured in any comet anywhere. It's 16 times greater than what we'd expect at that distance from the sun. This single measurement tells us that 3IATLAS formed in a place unlike anywhere in our solar system. A world so cold, so distant from its parent star, that carbon dioxide ice was more abundant than water ice when this comet was born billions of years ago. To understand why this matters so profoundly, we need to talk about how planetary systems form. When a star is born from a collapsing cloud of gas and dust, it's surrounded by a rotating disk of leftover material, a protoplanetary disk. This disk has a temperature gradient hot near the young star, progressively cooler as you move outward. Different molecules condense into ice at different temperatures. Water ice, the kind we're familiar with, condenses at around 170 Kelvin, about minus 150 degrees Fahrenheit. That's cold by Earth standards, but relatively warm in astronomical terms. In our solar system, the snow line, where water ice could form, is around 2.7 astronomical units from the sun, roughly between Mars and Jupiter. And carbon dioxide is different. CO2 ice condenses at lower temperatures around 60 to 80 Kelvin, depending on pressure. That's minus 315 to minus 280 degrees Fahrenheit. In our solar system's early history, the region where CO2 ice dominated was much farther out, perhaps 30 to 40 astronomical units in what we now call the Kuiper Belt. Carbon monoxide is even more volatile, condensing at around 25 Kelvin, just 25 degrees above absolute zero. That's so cold that helium remains liquid at such temperatures. In our solar system, carbon monoxide ice would have been dominant only in the most distant frigid regions of the protoplanetary disk. Now, comets from our solar system typically form in the outer regions in the Kuiper Belt, or the more distant Oort cloud. They do contain carbon dioxide and carbon monoxide, but water ice is usually the dominant volatile. When these comets warm up as they approach the sun, water sublimation drives most of their activity. The typical CO2 to H2O ratio in solar system comets is around 0.5 to 1, meaning equal amounts or slightly less CO2 than water. Some unusually CO2-rich comets might reach ratios of 2 or 3 to 1, but 8 to 1. That's unprecedented. What does this tell us about where 3IATLAS formed? It suggests the comet originated in a region of its parent protoplanetary disk that was extremely cold, much colder than the analogous regions in our solar system. Perhaps the parent star was smaller and cooler than our sun, producing less heat. Perhaps 3IATLAS formed at a much greater distance from its star, out in the equivalent of our Oort cloud, or beyond. Or perhaps the protoplanetary disk itself had unusual chemistry, with an overabundance of carbon relative to oxygen. Stellar chemistry varies throughout the galaxy. Our sun is what astronomers call a population 1 star, relatively young at 4.6 billion years old, with a healthy abundance of heavy elements. These heavy elements, everything heavier than hydrogen and helium, were created in previous generations of stars and distributed through the galaxy by supernova explosions. But not all stars have the same composition. Older stars, particularly those in the thick disk of the Milky Way, formed earlier in galactic history when fewer supernovae had occurred, meaning they have lower metallicity, less carbon, oxygen, nitrogen, silicon, iron, and so on. If 3IATLAS originated from a thick disk star system, its parent star and protoplanetary disk would have had different elemental ratios than our sun. The carbon-to-oxygen ratio, in particular, can vary significantly. In carbon-rich environments, you get more carbon-bearing molecules like CO2, CO, and methane. In oxygen-rich environments like our own solar system, water dominates. The chemistry of 3IATLAS suggests it may have formed in a relatively carbon-rich system, or at least in a region of its disk, where carbon compounds were preferentially incorporated into ices. But the story doesn't end with carbon dioxide. Spectroscopic observations from multiple facilities. The Gemini South Telescope in Chile, NASA's Infrared Telescope facility in Hawaii, the European Southern Observatory's Very Large Telescope in Chile, all contributed pieces to the chemical puzzle. Water ice was confirmed on July 20, 2025, from near-infrared observations. This was expected. Even with the unusual CO2 dominance, water should still be present. What surprised researchers was when it showed up. Water ice sublimates effectively only when surface temperatures rise above about 170 Kelvin. For a comet at 3IATLAS's distance in July, you wouldn't expect strong water signatures. Yet, there they were, clear absorption features at wavelengths characteristic of water ice and water vapor. The comet was warming up faster than models predicted, or its surface was darker and more efficient at absorbing heat, or jets of gas were exposing fresh icy material from beneath the surface. Carbon monoxide was also detected, though, in smaller quantities than CO2. This makes sense from a temperature standpoint. CO is so volatile that much of it may have already escaped during the comet's long journey through interstellar space, slowly sublimating even in the near absolute zero cold of the interstellar medium over millions of years. What remains is probably locked in deeper layers, protected by the outer crust of less volatile ices. Then there's cyanide-specifically molecular emission features consistent with CN radicals, fragments of larger molecules broken apart by solar ultraviolet light. Cyanide is a common cometary molecule despite its sinister reputation on Earth. It forms naturally in the cold chemistry of molecular clouds and protoplanetary disks. Its presence in 3IATLAS confirms that the comet contains organic compounds, carbon-nitrogen bonds, that are the building blocks of more complex molecules. Every comet we've studied contains organics. 3IATLAS is no exception in this regard. But here's where things get truly fascinating: the nickel. Observations from the Very Large Telescope using high-resolution spectroscopy detected emission lines from gaseous nickel atoms in the coma of 3IATLAS. Not nickel dust, but individual nickel atoms, floating in the gas phase, having been somehow liberated from the comet's solid material. Normally, metals like nickel and iron are locked up in silicate minerals and dust grains. They don't easily vaporize because they have very high sublimation temperatures. You need around 3,000 Kelvin to turn solid nickel into nickel gas. Yet there it was detectable in the comet's coma when 3IATLAS was still relatively far from the sun. Even more intriguing was the nickel-to-iron ratio. In solar system comets, when you do detect gaseous metals, which is rare and requires very sensitive instruments, the ratio of nickel to iron is fairly consistent, reflecting the cosmic abundance ratios and the similar chemistry of these two elements. But in 3IATLAS, the nickel-to-iron ratio appeared elevated higher than expected. Why one possibility is that the parent star system had slightly different nucleosynthetic history. Nickel and iron are both produced in supernova explosions, but different types of supernova produce them in different ratios. Type Ia supernovae, exploding white dwarf stars, produce lots of iron. Core collapse supernovae, massive stars exploding at the end of their lives, produce more balanced mixtures of elements. If the molecular cloud that formed 3IATLAS's parent star was enriched by a particular mix of supernova types that could explain the unusual ratio. Another possibility is that the release mechanism is selective. Perhaps organic molecules or other compounds in the comet can complex with nickel more easily than iron, allowing nickel to be liberated into the gas phase more efficiently. Or perhaps the dust grain structure is such that nickel-bearing minerals sublimate at slightly lower temperatures than iron-bearing ones. These are subtle effects, but they matter because they give us clues about the detailed mineralogy and chemistry of this ancient object. Spectroscopy and the optical wavelengths, visible light revealed more surprises. Observations from the Southern African Large Telescope and the Nordic Optical Telescope showed what's called the reflectance spectrum, how much light of each color is reflected by the comet's dust. Most solar system comets show what's called a red slope. They reflect slightly more red light than blue light, giving them a subtle reddish color. This reddening is thought to come from organic compounds, complex carbon-based molecules that have been processed by radiation over time. These organics coat the dust grains and absorb blue light preferentially. 3IATLAS showed a spectral slope of 22.8% per micrometer in the 400 to 700 nanometer range. That's the optical wavelengths our eyes can see. This means for every micrometer increase in wavelength from blue toward red, the reflectance increases by about 23%. That's steep. That's very red. It's consistent with a surface rich in organic materials, possibly even more so than typical solar system comets. These organics likely formed in the cold outer regions of the parent protoplanetary disk, where UV radiation from the young star and cosmic rays processed simple molecules into increasingly complex compounds over millions of years. The result is a dark reddish surface coating that tells a story of chemical evolution in another star system. Think about what organic-rich materials mean in a broader context. Organic molecules, compounds containing carbon, bonded to hydrogen, oxygen, nitrogen, and other elements are the chemical foundation of life as we know it. Comets in our solar system delivered vast quantities of organic compounds to the early Earth, potentially providing some of the raw materials for the origin of life. If 3IATLAS is rich in organics, it suggests that the chemical pathways leading to complex carbon compounds are not unique to our solar system. They're universal, or at least common, across planetary systems in our galaxy. Every star system may be seeding its planets with organic chemistry through cometary impacts. But let's return to that 8:1 ratio of CO2 to water, because it deserves deeper consideration. This ratio isn't constant. It changes as the comet moves closer to the Sun. In August, when James Webb made its observations, 3IATLAS was about 5 astronomical units from the Sun, roughly the distance of the asteroid belt. At that distance, both CO2 and water ice can sublimate if the surface temperature is right. As the comet continued inward toward its October perihelion, the ratio evolved. More water began to be released as surface temperatures climbed. By the time of perihelion, preliminary data suggested the ratio had decreased to perhaps 4 or 5:1, still extraordinarily high, but not as extreme as in August. This evolution tells us about the comet's structure. Comets aren't uniform spheres of ice. They're more like layered heterogeneous mixtures of different ices, dust, and organic compounds. The outermost layers, which sublimate first when the comet is still far from the Sun, may be dominated by the most volatile ices, CO and CO2. As these layers burn away, deeper layers are exposed, which may have different composition, perhaps richer in water ice. The fact that the CO2 to H2O ratio decreased as 3IATLAS approached the Sun suggests exactly this kind of layered structure, with a CO2-rich mantle overlying a more water-rich interior. Or perhaps the comet is simply heterogeneous, with some regions dominated by CO2 and others by water, and as it rotates and different regions are illuminated by sunlight, the overall composition of the released gas shifts. The 16-hour rotation period measured through brightness variations supports this idea of an irregularly shaped rotating nucleus, exposing different surface compositions to sunlight over time. Now, let's compare this chemistry to the other two interstellar visitors we've studied. Oumuamua, the first detected in 2017, remains deeply puzzling. It showed no obvious cometary activity, no visible coma or tail, despite passing very close to the Sun. Its chemical composition remains largely unknown because we couldn't observe it long enough to do detailed spectroscopy. Some researchers have suggested it might have been unusually dry, perhaps having lost its volatile ices during millions of years in interstellar space, leaving behind a rocky or possibly metallic core. Others have proposed more exotic explanations. Without direct compositional data, Oumuamua remains an enigma. 2I Borisov, discovered in 2019, was more conventional. It displayed clear cometary activity and was observable for months as it passed through the inner solar system. Spectroscopic studies revealed it was rich in carbon monoxide. The CO2-H2O ratio was around 2:1. Making it one of the most CO-rich comets ever observed, interstellar or otherwise. This suggested Borisov formed in a very cold region of its parent system, cold enough for CO ice to be abundant. But its overall behavior and other chemical signatures were similar to the most pristine comets in our own Oort cloud. Borisov was unusual, but not inexplicable. 3IATLAS is different again. CO2 dominance instead of CO or water, extremely high activity for its distance, unusual metal ratios, strong organic signatures. If each interstellar object is weird in a different way, 3IATLAS is expanding our understanding of just how diverse planetary system chemistries can be. This diversity shouldn't surprise us, yet somehow it does. For so long, we had only our solar system as an example. We assume, perhaps unconsciously, that other systems would be similar. The discovery of exoplanets starting in the 1990s began to challenge that assumption. We found hot Jupiters orbiting closer to their stars than Mercury orbits our sun systems, with multiple super-Earths planets in orbits that defy our expectations. Now, interstellar objects are teaching us that even small bodies, comets, and asteroids show remarkable diversity across the galaxy. Consider the implications for planetary habitability and the origin of life. If comets deliver organic compounds and volatiles to young planets, and if different star systems produce comets with wildly different chemistries, then every planet receives a different cocktail of ingredients. Earth received the blend provided by solar system comets, water-rich, with moderate amounts of CO2, CO, and organics. A planet in 3IATLAS's home system would receive comets dominated by CO2 with abundant organics, but perhaps less water. How would that affect the potential for life? Would life arise more easily, less easily, or simply differently? We don't know. We're only beginning to ask these questions. But every interstellar object we study gives us one more data point, one more example of how nature can arrange the elements. There's something profound about analyzing the chemistry of an object that formed 7 to 14 billion years ago in another star system. The photons of light captured by our telescopes left the surface of 3IATLAS just minutes ago. But the molecules those photons interacted with have been frozen essentially unchanged for eons. The CO2 ice sublimating today was laid down in a protoplanetary disk so long ago that the universe was a different place. The first galaxies were still forming. The Milky Way was younger, smaller. The Sun didn't exist. Earth didn't exist. And yet, here is this ancient ice preserved across billions of years and trillions of miles, now warming in our Sun's light and revealing its secrets to our instruments. What else might we learn if we could analyze 3IATLAS up close? If we could land on its surface, drill into its ice, analyze samples in a laboratory? The chemistry we're detecting now comes from the outermost layers, the material most affected by radiation exposure during its interstellar journey. Deep inside the nucleus protected from cosmic rays and UV light, the ice might be even more pristine, containing molecules that have been utterly unchanged since the comet's formation. Amino acids, perhaps, complex organics, maybe even prebiotic compounds. We'll never know not with this comet. It's moving too fast, and we had no warning of its arrival. By the time we could design, build, and launch a spacecraft to intercept it, 3IATLAS will be long gone. But the knowledge we're gaining from remote observations is already invaluable. We're learning what's possible in the universe's chemistry lab. We're expanding our catalog of what comets can be, what planetary systems can produce, and we're building the knowledge base that will inform future missions, like ESA's Comet Interceptor, scheduled to launch in 2029, which will wait in space for the next interstellar visitor and attempt a high-speed flyby, capturing close-up images and direct samples of gas and dust. The chemistry of 3IATLAS is a message from another world. It's written in the language of spectral lines and molecular ratios, in emission features and reflectance spectra. Decoding that message requires sophisticated instruments, complex analysis, and deep understanding of chemistry and physics. But the effort is worthwhile because the message tells us we're part of a galaxy teeming with diverse chemistry, with planetary systems that explore different evolutionary pathways with ices and organics, formed under conditions we're only beginning to understand. Yet chemistry alone doesn't fully explain the mystery of 3IATLAS. Knowing what it's made of is crucial, but understanding how it behaves, why it's so active, why it brightened unexpectedly, why it seems to be changing faster than predictions, requires us to look at something else entirely. The forces acting on this ancient traveler as it races through our solar system. And those forces are revealing phenomena that challenge our models in unexpected ways. Imagine you're tracking an object moving through space, carefully plotting its position, night after night, calculating its trajectory based on the sun's gravitational pull. Your equations are precise, accounting for the inverse square law of gravity, the orbital mechanics refined since Newton's time. The math predicts exactly where the object should be at any given moment. And then, one night you look through the telescope and find it's not quite where it should be. It's moved slightly faster than pure gravity would allow, accelerated by an invisible force your equations didn't include. This is what happened with 3IATLAS throughout the summer and fall of 2025. The comet was experiencing what astronomers call non-gravitational acceleration, forces beyond gravity that were subtly but measurably changing its trajectory. These forces were causing it to speed up, to brighten unexpectedly, to behave in ways that challenged every prediction. And locked within this mysterious acceleration is the key to understanding why 3IATLAS is so profoundly different from anything we've encountered before. Before we dive deeper into this cosmic mystery, I just want to take a moment to thank you for being here, for exploring these questions with me. If you're finding this journey through the cosmos as fascinating as I am, a like helps this video reach other curious minds, and subscribing means we can continue exploring together. Whether you're wide awake or drifting peacefully towards sleep, you're exactly where you're meant to be. Let's start with a fundamental question. What makes a comet move? The obvious answer is gravity. The sun's immense mass, about 333,000 times the mass of Earth, creates a gravitational well that dominates the solar system. Every object from the largest planet to the smallest dust grain moves primarily under the sun's gravitational influence. Newton's law of universal gravitation, refined by Einstein's general relativity for extreme cases, predicts these motions with remarkable precision. When astronomers calculate orbits, they include gravitational effects from all the major planets as well, because Jupiter's mass alone is enough to perturb the trajectory of comets passing through the inner solar system. But comets have a secret. They're not inert rocks. They're active bodies made largely of ice. As a comet approaches the sun and warms up, those ices sublimate, transforming directly from solid to gas without passing through a liquid phase. This process doesn't happen evenly across the surface. Some regions are more active than others, perhaps because they contain more volatile ices, or because the ice is less contaminated with dust, or simply because they're pointed toward the sun and receiving more solar heating. When ice sublimates, the gas doesn't just drift away peacefully. It erupts in jets, fountains of vapor escaping at speeds of hundreds of meters per second, carrying dust particles along with it. Here's where it gets interesting. When gas jets erupt from one side of a comet, they create thrust, a rocket effect. Just as a rocket engine propels a spacecraft by expelling exhaust in one direction, a comet's outgassing jets push the nucleus in the opposite direction. If the jets are symmetric, evenly distributed around the comet, the forces cancel out. But if they're asymmetric, stronger on one side than the other, or concentrated in specific regions, they create a net force that changes the comet's trajectory. This is non-gravitational acceleration. The effect is small. We're not talking about dramatic course changes. A typical comet might experience non-gravitational accelerations on the order of 0.1% of the sun's gravitational pull. But over weeks and months, these tiny forces accumulate. The comet ends up slightly ahead of or behind where pure gravitational calculations would place it. Measuring this deviation allows astronomers to estimate how much outgassing is occurring, which in turn tells us about the comet's activity level and composition. 3IATLAS began showing measurable non-gravitational acceleration shortly after its discovery. By late July 2025, when several weeks of positional data had accumulated, orbit specialists noticed the discrepancy. The comet was arriving at predicted positions a bit early, suggesting it was accelerating along its orbital path. This acceleration wasn't constant. It varied as the comet's distance from the sun changed and as its rotation brought different surface regions into sunlight. The magnitude of this acceleration provided crucial information about the comet's size. Here's the logic. The thrust from outgassing depends on how much gas is being released, which depends on the surface area actively sublimating, but the resulting acceleration depends on the comet's mass. Newton's second law force equals mass times acceleration. A small low-mass comet will experience greater acceleration from the same amount of outgassing than a large massive comet. By measuring the non-gravitational acceleration and estimating the outgassing rate from spectroscopic observations, researchers could constrain the nucleus size. The calculation suggested an upper limit on the nucleus diameter of about 3.5 miles, 5.6 kilometers, with a lower limit around 1/400 feet or 440 meters. That's quite a range from roughly the length of 5 football fields up to a mountain-sized object. The uncertainty comes from not knowing the exact density of the nucleus, the precise outgassing rate, or how efficiently the gas jets convert sublimation into thrust. But even with these uncertainties, we know 3IATLAS is a relatively small comet compared to some of the giants in our solar system. Comet Hale-Bopp, for instance, had a nucleus estimated at 40 kilometers across nearly 10 times larger. Yet despite its modest size, 3IATLAS was extraordinarily active. The dust mass loss rate, the amount of solid material streaming off the comet every second, ranged from 0.3 to 4.2 kilograms per second, depending on the comet's distance from the Sun and its current activity level. To put that in perspective, 4.2 kilograms per second is about 9 pounds per second, or roughly 775 pounds per minute, or 23 tons per day at peak activity. Over weeks, that adds up. Over months, it's transforming the comet, literally carving away layers of ice and dust, reshaping the nucleus, exposing fresh material from beneath. This level of activity at the distances 3IATLAS was traveling is remarkable. Remember in May, when TESS observed it, the comet was 6.4 astronomical units from the Sun, about 600 million miles. At that distance, solar heating is minimal. The amount of sunlight reaching the comet is only about 2.4% of what Earth receives. Surface temperatures might be around 120 to 130 Kelvin, cold enough that water ice should be stable and inert. Yet 3IATLAS was already active, already releasing gas and dust, already displaying a measurable coma. The only way this makes sense is if the comet contains extremely volatile ices that sublimate at very low temperatures. We've already discussed the high CO2 content, but carbon monoxide is even more volatile. CO ice sublimates at temperatures as low as 70 Kelvin, well below what water ice can tolerate. If 3IATLAS has significant amounts of CO ice at or near its surface, that CO would begin sublimating as soon as the comet received even minimal solar heating. This early onset activity suggests that the comet's outer layers are dominated by these supervolatiles. As 3IATLAS moved closer to the Sun through June, July, and August, solar heating intensified. At 4 astronomical units, about 370 million miles, the surface temperature would climb to perhaps 140 to 150 Kelvin. This is the threshold where CO2 ice begins to sublimate vigorously. The comet's activity should have increased smoothly and predictably as it warmed. But that's not what happened. In late September, citizen scientists using the interstellar network noticed something unexpected. The comet's brightness was increasing faster than the smooth curve predicted by standard models. It wasn't gradual. There was a surge, a sudden increase in luminosity that suggested a jump in activity. Cometary brightness is driven primarily by dust, scattering sunlight. The more dust in the coma, the brighter the comet appears. A brightness surge means more dust is being released, which in turn means more gas is sublimating to carry that dust into space. What could cause such a surge? One possibility is that the comet's rotation brought a particularly active region, perhaps a patch rich in volatile ices, into sustained sunlight for the first time. As that region heated up, it began outgassing, vigorously releasing more material than the average surface area would produce. Another possibility is that an insulating layer of dust on the surface suddenly gave way, exposing fresh ice beneath. Comets often develop a crust of non-volatile material dust and refractory organics that insulates the underlying ice. If this crust cracks or is blown away by gas pressure from below, the newly exposed ice can rapidly sublimate, causing an outburst. Outbursts are common in comets. They're sudden, short-lived increases in activity that can make a comet brighten by a factor of 2 or more within hours or days. Sometimes they're triggered by thermal stress cracking the surface. Sometimes they're caused by cliff collapses or landslides on the nucleus, which, despite being in microgravity, can still occur due to structural failure of the weakly bound icy material. Sometimes they're driven by subsurface gas pockets building up pressure and then explosively venting. The brightness surge observed in 3IATLAS in September wasn't necessarily a single outburst. It might have been a more sustained increase in activity as the comet's composition, those volatile-rich outer layers, responded to increasing solar heating. But the fact that it exceeded predictions suggests there's something about the physical structure or composition of 3IATLAS that standard cometary models don't capture. As October approached and the comet neared perihelion, its closest approach to the Sun, tracking its position, became more challenging from Earth because it was moving towards solar conjunction, the point where it passes nearly behind the Sun from our perspective. Ground-based telescopes can't observe objects too close to the Sun in the sky. The brightness overwhelms everything, but space-based solar observatories stepped in. NASA's Stereo spacecraft and the joint ESA-NASA SOHO mission, both designed to monitor the Sun, have cameras that can observe regions near the solar disk. They tracked 3IATLAS through late September and October, watching as it rounded the Sun. These observations confirmed what the citizen scientists had detected: the comet remained brighter than predicted. It was still outgassing vigorously, still releasing dust, still active at levels exceeding models. On October 29, 2025, at 11:44 UTC, 3IATLAS reached perihelion, passing 1.356 astronomical units from the Sun, about 126 million miles, roughly between the orbits of Earth and Mars. At that moment, it was traveling at its maximum speed of 68.3 kilometers per second, about 153,000 miles per hour. For reference, Earth orbits at 30 kilometers per second, so 3IATLAS was moving more than twice as fast as our planet. This tremendous speed is partly due to the Sun's gravity. Objects move faster when closer to the Sun, following Kepler's laws. But remember, 3IATLAS is on a hyperbolic trajectory. It's moving faster than escape velocity. Even at perihelion, even at the point where the Sun's gravity is pulling hardest, the comet still has enough kinetic energy to escape the solar system entirely. When it eventually crosses back out beyond Neptune's orbit and into interstellar space, it will still be traveling at about 57 kilometers per second, relative to the Sun, the same speed it had when it arrived. The Sun's gravity borrowed some speed as the comet fell inward, and it will take back that speed as the comet climbs back out. But the comet's fundamental excess velocity remains unchanged. That excess velocity, technically called hyperbolic excess velocity, or velocity at infinity, is the signature of interstellar objects. It tells us that 3IATLAS is not bound to. Our Sun was never bound to our Sun, and will never be bound to our Sun. It's just passing through, briefly influenced, but fundamentally independent. Now, let's talk about the comet's rotation, because it factors into the acceleration story. Observations of brightness, variations, how the comet's apparent luminosity changes over time, revealed a periodic pattern with a period of 16.16 hours. This is the rotation period, the time it takes for the nucleus to spin once on its axis. The amplitude of the brightness variation was about 0.3 magnitudes, meaning the comet appeared roughly 30% brighter at its brightest compared to its faintest. This tells us the nucleus is not spherical. A perfectly round object would look the same regardless of which side was facing us. Its brightness wouldn't vary as it rotates. The fact that 3IATLAS brightens and dims indicates an elongated or irregular shape similar to a potato, or perhaps a contact binary, two lobes stuck together. As it rotates, we see more or less surface area or regions with different reflectivity, causing the brightness to oscillate. The 16-hour rotation is relatively slow for a small comet. Some comets rotate in just a few hours, others take days. The rotation rate depends on the nucleus's formation, history, any collisions it experienced, and the torque supplied by outgassing jets. Those same jets that create non-gravitational acceleration also exert torques, gradually spinning the nucleus up or down, depending on the geometry of the active regions. Here's where rotation becomes important for understanding the comet's behavior. As 3IATLAS rotates, different regions of its surface move in and out of sunlight. The subsolar point, the spot where the Sun appears directly overhead, migrates across the surface over the course of each 16-hour rotation. Regions enter daylight heat, up begins sublimating. Then they rotate into darkness, cool down, and activity ceases. This creates a complex, time-varying pattern of outgassing. The total activity at any moment is the sum of contributions from all the sunlit regions, each with potentially different compositions and ice contents. If one hemisphere of the nucleus is richer in volatile ices than the other, perhaps due to how the comet formed, or perhaps because one side was preferentially eroded during previous close encounters with stars or planets, then the comet's activity will vary with rotation. This could explain some of the unexpected brightening, as particularly volatile-rich regions rotated into sunlight. For the first time in millions of years, they erupted in enhanced activity, producing more dust and gas than the average surface. There's another factor to consider: the Yarkovsky effect. This is a subtle but real force that affects rotating objects in space. As a rotating body absorbs sunlight and heats up, it later radiates that energy as infrared light when the surface cools. But because of rotation, the warmest parts of the surface are slightly displaced from the subsolar point. They're carried forward by rotation before they can fully cool. This creates an asymmetry in thermal emission, which exerts a tiny recoil force on the object. For small asteroids and comets, the Yarkovsky effect can measurably alter orbits over long timescales. For 3IATLAS, the Yarkovsky effect is probably negligible compared to outgassing jets, but it's worth mentioning because it illustrates how many subtle forces are at play. Calculating a comet's trajectory isn't as simple as plugging numbers into Newtonian gravity equations. You must account for solar radiation, pressure, photons from the sun striking dust grains and imparting momentum. You must account for outgassing thrust, which varies with distance, rotation, and surface composition. You must account for planetary perturbations. And you must accept that there's always uncertainty because comets are chaotic, unpredictable beasts. The acceleration of 3IATLAS also raises questions about its long-term evolution. Every gram of material lost to space is mass that can never be recovered. Over the weeks and months of its passage through the inner solar system, 3IATLAS has shed countless tons of ice and dust. This mass loss changes the comet. It makes it smaller, alters its shape, reduces its gravitational field. If the mass loss is uneven, more active on one side than the other, it can shift the center of mass, which in turn affects the rotation. It's a feedback process. Activity affects rotation, rotation affects activity. Both affect the trajectory. Some comets don't survive perihelion passage. The thermal stress, the intense outgassing, the structural weakness of the loosely bound nucleus, all these factors can cause fragmentation. The comet can split into multiple pieces, each following slightly different trajectories. We've seen this happen many times. Comet Shoemaker-Levy 9, which famously collided with Jupiter in 1994, had already fragmented into more than 20 pieces during a previous close approach to Jupiter. Comet 73P Schwarzmann-Bachmann 3 has been observed breaking apart over multiple apparitions. Did 3IATLAS survive perihelion intact? The observations suggest yes, though it's difficult to be certain. No obvious fragments were detected in images captured shortly after perihelion by spacecraft and space telescopes. The coma remained centrally concentrated, consistent with a single nucleus rather than multiple fragments spreading apart. But the comet's continued high activity suggests it's still actively losing mass, still evolving, still changing as we watch. Think about the violence of what's happening on the surface of 3IATLAS. Ice sublimating at speeds of hundreds of meters per second, gas jets erupting with enough force to lift dust particles, some weighing milligrams, some micrograms off the surface and fling them into space. The surface temperature at perihelion could reach 200 Kelvin or higher in directly sunlit regions, warm enough that water ice becomes quite active, joining the CO2 and CO in a frenzy of sublimation. Dust grains, once embedded in ice, are liberated and accelerated outward, forming the coma and tail that make comets visible. Larger chunks, pebbles, perhaps small boulders might also be lifted off if they're small enough, and the gas velocity is high enough. This is why comets leave debris trails in their wake. As they orbit the sun, they continuously shed dust. This dust spreads out along the orbital path, forming a river of particles. When Earth's orbit intersects one of these debris trails, we experience meteor showers, hundreds or thousands of tiny grains burning up in our atmosphere, creating streaks of light across the night sky. 3IATLAS is leaving its own trail, but will never cross it. Its orbit is so different from Earth's, so steeply inclined and so fast, that the debris trail will disperse into the vastness of space, never to encounter our planet. The acceleration, the activity, the unexpected brightness surge, all of these phenomena tell us that 3IATLAS is not behaving like a typical comet, even by interstellar standards. 2I Borisov, our previous interstellar comet visitor, was active but relatively well behaved. Its behavior largely matched predictions based on solar system comets. 3IATLAS is different. It's more active at greater distances. Its composition is more extreme. Its brightness evolution is harder to predict. It's teaching us that the diversity of cometary behavior is even greater than we thought. This brings us to a philosophical point. Every object we study expands our understanding of what's possible in nature. Before 3IATLAS, we might have assumed that CO2-dominated comets couldn't sustain such high activity at such large distances. Now, we know they can. Before we measured its non-gravitational acceleration, we might have underestimated how much thrust can be generated by supervolatile outgassing. Now we have data to refine our models. This is how science progresses, not by confirming what we already believe, but by encountering phenomena that challenge our assumptions and force us to think more deeply. But all of this activity, all of this acceleration and changing behavior exists within a larger context, the comet's journey through our solar system. Where has it been? Where is it going? What paths has it traced past our planets? Understanding 3IATLAS's grand tour through our celestial neighborhood reveals even more about this mysterious visitor and the fleeting window we have to study it. Picture a visitor from another star system entering our cosmic neighborhood, sweeping past our worlds on a trajectory that will never bring it back. In the span of just a few months, Atlas traced an arc through the inner solar system that brought it near Mars, past Mercury, within viewing range of Venus, and eventually to its closest approach to Earth on December 19th. Each planetary encounter was a unique opportunity, a chance to observe this ancient traveler from different vantage points, to measure it with different instruments, to capture its changing appearance as it moved through varying distances from the sun. But here's what makes this journey so remarkable. The comet's path was choreographed by pure gravitational mechanics. Yet it unfolded like a carefully planned tour, bringing it into range of more spacecraft, more telescopes, and more observation platforms than any previous interstellar object. The cosmic ballet of 3IATLAS through our solar system is a story of perfect timing, unexpected proximity, and the fleeting nature of these once-in-a-lifetime encounters. If this journey through our solar system captivates you as much as it does me, I'd be grateful if you'd let me know with a like. And if you're curious about where this story goes, next subscribing means you'll be here for every discovery, every revelation, every moment of wonder. Whether you're listening wide awake or drifting gently toward dreams, you're part of this exploration. Let's trace the path. When 3IATLAS was first detected on July the 1st, 2025, it was already deep within the solar system. 4.51 astronomical units from the Sun, approximately 420 million miles, located between the orbits of Mars and Jupiter. It was moving inward at tremendous speed, roughly 61 kilometers per second, heading toward the inner solar system on a trajectory that would bring it inside Mars's orbit by autumn. But its journey had begun much earlier, long before we noticed it. Working backward from the Discovery observations, astronomers reconstructed 3IATLAS's path through the outer solar system. It crossed Neptune's orbit about 30 astronomical units from the Sun sometime in early 2024, more than a year before we detected it. At that distance, it would have been incredibly faint, perhaps magnitude 24 or 25, far too dim for any telescope to spot, unless you knew exactly where to look. It would have taken the comet roughly 10 months to travel from Neptune's orbit to Jupiter's orbit, gradually accelerating under the Sun's gravitational pull. By December 2024, 3IATLAS was crossing Jupiter's orbital distance about 5.2 astronomical units from the Sun. Still undetected, still invisible, it continued inward through the spring of 2025. The TESS observations from May 7th through June 3rd captured it at around 6. 4AU making those observations some of the earliest records of the comet when it was already showing activity far beyond normal expectations. Then came the discovery in early July, and the race was on to observe it from every possible platform before it became too difficult to track. The first major milestone in its planetary encounters occurred on October 3, 2025, when 3IATLAS made its closest approach to Mars, 0.194 astronomical units, or about 19 million miles. In celestial terms, that's remarkably close. For comparison, Mars at its nearest to Earth is still about 35 million miles away. The comet was passing Mars at roughly half that distance. This proximity created an extraordinary opportunity. NASA operates 3 spacecraft in orbit around Mars Reconnaissance Orbiter, MAVEN, and the Perseverance rover on the surface with its MOSCAM/Z camera. ESA's Mars Express and ExoMars Trace Gas Orbiter were also in position along with China's Tianwen-1 mission. These spacecraft were designed to study Mars, not to observe distant comets, but mission planners quickly realized they could reprogram observation schedules to capture this once-in-a-lifetime target. The challenges were significant. These spacecraft carry cameras and instruments optimized for imaging Mars from distances of just a few hundred to a few thousand kilometers. Suddenly, they were being asked to photograph an object 30 million kilometers away, 10,000 times farther than their typical targets. It's like trying to use a microscope to photograph a distant mountain. The instruments weren't designed for it, but the opportunity was too precious to miss. Mars Reconnaissance Orbiter's HiRISE camera. The high-resolution imaging science experiment, capable of resolving features on Mars as small as a desk, captured 3IATLAS on October 2nd, one day before closest approach. The comet appeared as a small fuzzy blob, its coma clearly visible even at that enormous distance. The image spans about 30 million kilometers, an almost incomprehensible scale. Yet there in the frame is this visitor from another star system, glowing softly against the black background of space. MAVEN, the Mars, Atmosphere and Volatile Evolution spacecraft observed 3IATLAS using its imaging ultraviolet spectrograph. This instrument is designed to study Mars's upper atmosphere by observing ultraviolet light, but it's also sensitive to hydrogen emission from comets. The images MAVEN captured on September 28th, just days before closest approach, revealed a vast hydrogen cloud surrounding the comet. This hydrogen comes from the breakup of water molecules and hydroxyl radicals in the coma, dissociated by solar UV radiation. The hydrogen atoms then scatter UV light, making them visible to MAVEN's spectrograph. The cloud extended far beyond the visible coma, showing just how much material was streaming off 3IATLAS. On Mars's surface, the Perseverance rover pointed its MOSCAM-Z instrument toward the sky and captured images of 3IATLAS on October 4th. From the surface looking up through Mars's thin atmosphere, the comet appeared as a faint smudge against the starfield. The rover was exploring the rim of Jezero crater, at the time searching for signs of ancient microbial life in rocks formed billions of years ago when Mars had liquid water on its surface. To pause that historic mission and photograph an interstellar visitor adds a poetic layer to the moment studying ancient Mars, while documenting an even more ancient traveler from the stars. ESA's ExoMars Trace, Gas Orbiter, and Mars Express also captured observations between October 1st and 7th. The CASIS camera aboard TGO color and stereo surface imaging system produced a sequence of images showing the comet as a slightly fuzzy white dot moving against the background stars. Michael Kuppers, project scientist for ESA's upcoming Comet Interceptor mission, noted that these observations from Mars provided crucial data for understanding how to design a rapid response mission to intercept an interstellar object in the future. Every observation, every image, every measurement adds to the knowledge base that will enable future missions. What did all these observations from Mars reveal? First, they confirmed the comet's trajectory with unprecedented precision. By observing from Mars while Earth-based telescopes simultaneously observed from our planet, astronomers created a parallax measurement, a triangulation, that nailed down the comet's position to within a few thousand kilometers. This improved orbital predictions by an order of magnitude, allowing much more accurate forecasting of where 3IATLAS would be in the following weeks and months. Second, the observations showed that the comet's activity remained strong at 1.8 AU from the Sun, Mars's approximate distance. The coma was prominent, the dust production was ongoing, and the hydrogen cloud indicated active water sublimation. This was crucial data for understanding the comet's composition and evolution. Just 5 days after passing Mars on October 8th, 3IATLAS made a more distant approach to Mercury, passing at 1.662 astronomical units, about 108 million miles. Mercury, being the innermost planet, orbits much faster than Mars. It completes one orbit in just 88 Earth days, compared to Mars's 687 days. The high orbital velocity meant that Mercury and 3IATLAS were moving in nearly perpendicular directions during the flyby, a brief celestial crossing, with no opportunity for close observation. No spacecraft currently orbit Mercury. NASA's MESSENGER mission ended in 2015, and ESA JAXA's Bepi-Colombo mission won't arrive until 2026. So, this encounter passed largely unobserved except from Earth-based telescopes, which could barely resolve the comet at that distance and angle. The next major milestone came on October 29, 2025 at 11:44 UTC perihelion. This was the moment 3IATLAS reached its closest point to the Sun, just 1.356 astronomical units, or roughly 126 million miles. For perspective, Earth orbits at 1 AU 93 million miles, so the comet was passing about 33 million miles farther from the Sun than we are. Mars orbits at 1.52 AU, meaning perihelion occurred just inside Mars's orbital distance. At perihelion, 3IATLAS was traveling at its maximum speed of 68.3 kilometers per second. The Sun's immense gravity had been accelerating the comet as it fell inward from the outer solar system, converting gravitational potential energy into kinetic energy. This is Kepler's second law. In action, objects sweep out equal areas in equal times, meaning they move faster when closer to the Sun. For 3IATLAS already traveling at enormous interstellar speeds, this additional gravitational boost pushed it to velocities that dwarf anything achieved by human spacecraft. Perihelion was also the point of maximum solar heating. The intensity of sunlight at 1.36 AU is about 54% of what Earth receives, not dramatically different, but enough to drive vigorous cometary activity. This is the moment when outgassing should peak, when dust production reaches maximum, when the comet is at its brightest and most active. And indeed, observations from space-based solar observatories like SOHO and Stereo confirmed that 3IATLAS brightened significantly around perihelion. But here's the challenge: from Earth perspective, perihelion occurred almost directly behind the Sun. The comet was in solar conjunction, meaning it was in the same direction as the Sun when viewed from Earth, Ground-based telescopes can't observe objects too close to the sun. The sky is too bright. The atmospheric distortion too severe. This is where space-based assets become invaluable. SOHO and stereo, positioned in different orbits, specifically to monitor the sun, could observe 3IATLAS even when it was angularly close to our star. These missions, designed primarily for solar physics, found themselves documenting an interstellar visitor at its most active moment. 5 days after perihelion, on November 3rd, 3IATLAS passed relatively close to Venus at 0.649 astronomical units, about 60 million miles. Venus orbits at 0.72 AU, so the comet crossed just inside its orbital path. Unfortunately, no active spacecraft orbit Venus currently. Japan's Akatsuki spacecraft is there, but its instruments are optimized for studying Venus's thick atmosphere and wouldn't be useful for observing a distant comet. So, like the Mercury encounter, this flyby was documented primarily from Earth-based telescopes, capturing data about the comet's appearance and activity in the days following perihelion. As November progressed, 3IATLAS emerged from solar conjunction and became observable again from Earth. It was now moving outward, heading back toward the outer solar system, but still close enough to study. The comet's appearance had changed. The dust tail, which had grown longer and more prominent as perihelion approached, was now at its most extended, stretching millions of kilometers behind the nucleus, as solar radiation pressure pushed dust particles outward. The coma remained bright, though activity was beginning to decline as the comet moved away from the sun and surface temperatures dropped. ESA's JUICE mission, the Jupiter Icy Moons Explorer, made observations of 3IATLAS in November, using several instruments, including cameras, spectrometers, and particle sensors. JUICE was launched in April 2023 and is currently on its long journey to Jupiter, where it will arrive in 2031 to study Ganymede, Callisto, and Europa. But in November 2025, JUICE happened to be positioned where it had a clear view of the comet. The observation wasn't planned years in advance. It was a target of opportunity scheduled in response to the comet's discovery. This flexibility, the ability to reprogram spacecraft to observe unexpected phenomena, is one of the hallmarks of modern space missions. The JUICE observations were particularly valuable because the spacecraft was relatively close to the sun compared to Earth, giving it a different viewing angle. Multi-spacecraft observations from various positions allow astronomers to build three-dimensional models of the coma structure, understanding how dust is distributed, how gas jets emanate from different regions of the nucleus, and how the tail develops. Each additional viewpoint adds depth to our understanding. This brings us to December 19th, 2025, the moment we've been building toward. On this date, 3IATLAS will make its closest approach to Earth at 1.798 astronomical units, approximately 167 million miles or 270 million kilometers. That's almost twice the distance between Earth and the Sun. In astronomical terms, this is close, much closer than any previous interstellar object has been to Earth during its discovery apparition. Oumuamua's closest approach was 0.16 AU on October 14, 2017, but it wasn't discovered until October 19th, 5 days after closest approach, when it was already receding. By the time astronomers realized what they were looking at, Oumuamua was gone. 2I Borisov made its closest approach to Earth in December 2019 at 1.9 AU, slightly farther than 3IATLAS, and was observable for months before and after that date. Why does December 19th matter if the comet is still 167 million miles away? Because it represents our optimal observation window. After this date, 3IATLAS will continue moving outward, and as the distance increases, it will fade. The apparent magnitude, how bright it appears from Earth, will drop. Right now, in early December, the comet is around magnitude 10 to 11, visible through modest amateur telescopes with apertures of 6 to 8 inches. By late December, it will have faded to magnitude 12 or 13, requiring larger instruments. By January, magnitude 14 or fainter, accessible only to serious amateur astronomers with large scopes and dark skies, or to professional facilities. The geometry on December 19th is significant for another reason: the comet will be on the opposite side of the Sun from Earth. This means it's observable in the night sky, not drowned out by solar glare. Its position near the constellation Leo, close to the bright star Regulus, makes it relatively easy to locate for observers who know where to look. Astrophotographers are planning imaging sessions, capturing what may be their only chance to photograph an object from another star system. Professional observatories are maximizing their time as well. The James Webb Space Telescope has scheduled post-perihelion observations in December to study how the comet's chemistry evolves as it moves away from the Sun. Do the volatile ices continue sublimating at high rates, or does activity drop off rapidly? How does the CO2 to H2O ratio change as the comet cools? Are there any delayed outbursts as subsurface ice is warmed during perihelion passage, finally rupture through to the surface? Ground-based facilities like the Very Large Telescope, Gemini Observatory, and Subaru Telescope are all contributing observations. Spectroscopy at multiple wavelengths, optical near-infrared, mid-infrared, provides the most complete picture of the comet's composition. Polarimetry measurements, studying how light reflected from the coma is polarized, reveal information about dust grain sizes and shapes. Radio observations can detect molecules like methanol, hydrogen cyanide, and formaldehyde, which don't have strong signatures in optical spectra, but are important tracers of cometary chemistry. Looking ahead, 3IATLAS will pass Jupiter's orbital distance on March 16, 2026, at 0.358 astronomical units from the giant planet about 33 million miles. This is farther than the Mars encounter, but still close enough that Jupiter's gravity will measurably perturb the comet's trajectory. Jupiter, with 318 times Earth's mass, is the solar system's gravitational heavyweight. Any object passing relatively close to Jupiter experiences a significant deflection. For 3IATLAS, this won't change the hyperbolic nature of its orbit. It will still escape, but it will slightly modify the comet's outbound direction and speed. After the Jupiter encounter, 3IATLAS will cruise outward through the outer solar system, crossing Saturn's orbit by late 2027 or early 2028, reaching Uranus's orbital distance by the early 2030s and Neptune by the mid-2030s. By then, it will be so faint, probably magnitude 25 or fainter, that even the most powerful telescopes will struggle to detect it. The comet will fade into obscurity, lost among the faint background galaxies and distant stars, indistinguishable from the billions of other faint points of light in the deep sky. But consider what this journey represents. In the span of less than 2 years, from mid-2024, when it crossed Neptune's orbit inward, to mid-2026, when it crosses Jupiter's orbit outward 3, Atlas will have traversed the realm of the planets. It will have passed closer to 4 worlds than many solar system comets ever do. It will have been observed by more spacecraft, more telescopes, and more instruments than any previous interstellar object. It will have provided data that will be analyzed for years, informing models of cometary composition, protoplanetary disk chemistry, and planetary system diversity. The trajectory of 3IATLAS is defined by mathematics, Newtonian gravity modified by Einstein's general relativity, perturbed by outgassing forces influenced by planetary masses. Yet, there's something almost purposeful about how perfectly it threaded through our observation network. The October approach to Mars, placing it in range of multiple orbiters. The perihelion timing that allowed space-based solar observatories to track it. The December approach to Earth at a distance close enough to study, but far enough to be perfectly safe. The March 2026 encounter with Jupiter, providing one last gravitational data point before the comet escapes beyond the reach of our instruments. Of course, there's no purpose or design, just the mechanics of gravity and motion, playing out according to physical law. But the coincidence is remarkable nonetheless. If 3IATLAS had arrived even 6 months earlier or later, the planetary alignments would have been different. The observation opportunities would have been fewer. The data quality might have been poorer. Timing in astronomy, as in life, is everything. This journey through our solar system also highlights how far our observation capabilities have advanced. In previous decades, an interstellar object like 3IATLAS might have been detected months after its closest approach, when it was already receding and faint. We might have gathered minimal data before losing it forever. But modern sky surveys, global telescope networks, rapid communication, and the growing fleet of spacecraft throughout the solar system have transformed our ability to respond to these rare events. The Vera Rubin Observatory, once fully operational, will likely detect several interstellar objects each year. Each one will trace its own unique path through our celestial neighborhood. Some will pass close to planets. Others will skim the outskirts of the solar system, barely interacting with our worlds. Some will be active comets. Others might be inert asteroids or objects so unusual we can't easily categorize them. Each trajectory will be different, each encounter unique, each observation campaign tailored to that specific visitor. But even with improved detection, even with better instruments and faster response times, there remains something fleeting and precious about these encounters. We cannot send a spacecraft to rendezvous with 3IATLAS. The speeds involved, 68 kilometers per second at perihelion, far exceed our current propulsion capabilities. The best we could hope for would be a high-speed flyby racing past, at tens of kilometers per second, with perhaps a few minutes or hours in close proximity. Valuable, yes, but nothing like the detailed long-term study possible with a mission that can match velocities and orbit alongside its target. This limitation is why remote observation remains so critical. Every spectrum, every image, every measurement captured from our vantage points in the solar system adds to our understanding. We're like naturalists observing a rare bird that appears briefly before flying away forever. We must gather what data we can during the narrow window of opportunity, knowing we'll never see this particular specimen again. Yet, there's beauty in that impermanence. The journey of 3IATLAS through our solar system is a reminder of the dynamic, ever-changing nature of the cosmos. Objects move, encounters occur, moments of proximity arise and then pass. We're privileged to witness this one, to document it, to learn from it. And while 3IATLAS will eventually vanish into the interstellar void, the knowledge it leaves behind endures. But witnessing this journey and understanding the trajectory are only part of the story. To truly appreciate what we're seeing, we need to know how we're seeing it. The extraordinary coordination of spacecraft, telescopes, and instruments that made this unprecedented observation campaign possible. From Mars orbit to deep space, from optical to infrared, from professional observatories to amateur backyard setups, the eyes trained on 3IATLAS represent one of the most comprehensive multi-platform observation efforts in astronomical history. Imagine coordinating 12 different spacecraft, scattered across hundreds of millions of miles of space, all turning to observe a single faint object moving through the solar system. Add to that ground-based telescopes on 6 continents space, telescopes orbiting Earth solar observatories designed to stare at the sun, and a global network of amateur astronomers contributing from their backyards. This is the observation campaign that unfolded for 3IATLAS, unprecedented in scope, collaborative in spirit, and opportunistic in execution. Never before has an interstellar object been studied by so many eyes simultaneously. Never before have we had spacecraft positioned at Mars instruments orbiting Earth and facilities throughout the solar system, all working in concert to capture data about a visitor from beyond. This campaign wasn't planned years in advance. It was assembled in weeks and months as mission planners and astronomers realized they were witnessing something extraordinary and had to act quickly before the opportunity vanished forever. If you're amazed by this level of coordination, by humanity's ability to pivot and respond to cosmic surprises, I'd love for you to show your appreciation with a like. And subscribing means you'll be part of future discoveries as they unfold. Who knows what the next interstellar visitor might reveal? Let's begin with the spacecraft, because they provided some of the most unique perspectives. The Mars Fleet. NASA's Mars Reconnaissance Orbiter, MAVEN and Perseverance, along with ESA's Mars Express and ExoMars Trace Gas Orbiter, gave us the closest views. But coordinating these observations required careful planning. Each spacecraft has a primary mission studying Mars's geology, atmosphere, climate history. Their observation schedules are typically planned months in advance, every minute allocated to specific science objectives. To insert comet observations meant reprioritizing, sometimes delaying other measurements, negotiating with science teams who had waited years for their particular data. Mission controllers had to solve practical problems. Mars orbiters have limited data storage. They can't continuously record everything they observe. They must compress images, buffer data, and wait for communication windows when they can transmit to Earth. Observing 3IATLAS meant allocating precious downlink bandwidth to comet data rather than Mars data. It meant repositioning spacecraft, rotating them to point instruments in directions they weren't normally pointed. For the Perseverance rover on Mars's surface, it meant taking time away from geology investigations to photograph the sky, a rover designed to look down, drilling into rocks, analyzing soil samples, suddenly asked to look up. The technical challenges were significant. The HiRISE camera on Mars Reconnaissance Orbiter, for instance, is designed to photograph Mars's surface from an altitude of 300 kilometers with enough resolution to see objects the size of a coffee table. Its field of view is narrow, its focus optimized for short distances. Pointing it at a comet 30 million kilometers away is like using a magnifying glass to look at the horizon. The camera can't focus properly at infinity. The comet appears slightly blurred, but even a blurred image of an interstellar object is invaluable. The fact that HiRISE could detect 3IATLAS at all could resolve its coma, could measure its brightness. That's testament to the sensitivity of the instrument and the skill of the operators. MAVEN's contribution was different. Its ultraviolet spectrograph isn't designed to take pretty pictures. It measures the intensity of UV light at specific wavelengths, building up spectral profiles that reveal the chemical composition of whatever is being observed. When pointed at 3IATLAS, MAVEN detected the Lyman alpha emission of hydrogen light at a wavelength of 121.6 nanometers, produced when hydrogen atoms are excited by solar UV, and then emit photons as they return to their ground state. This hydrogen comes from the dissociation of water molecules in the coma. UV photons from the sun strike H2O molecules, breaking them apart into hydrogen and hydroxyl radicals. The hydrogen then forms an enormous cloud around the comet, extending far beyond the visible coma, creating a halo detectable only at UV wavelengths. The images MAVEN produced showed this hydrogen envelope stretching hundreds of thousands of kilometers around 3IATLAS. This is important because it tells us about water production rates. By measuring the brightness of the hydrogen emission and applying models of how water dissociates and hydrogen disperses, scientists can estimate how many water molecules per second are sublimating from the nucleus. For 3IATLAS, preliminary estimates suggested water production rates of around 10^27 to 10^28 molecules per second during the Mars flyby period. That sounds like a huge number, and it is, but it's actually modest compared to really active comets. Comet Hale-Bopp at its peak was producing water at rates exceeding tenfold 30 molecules per second. The relatively modest water production from 3IATLAS, combined with the extremely high CO2 production, reinforces the unusual composition we discussed earlier. ESA's spacecraft contributed crucial data as well. The ExoMars Trace Gas Orbiter's CASIS camera captured sequences showing the comet moving against the background stars. These aren't dramatic images. The comet appears as a small, slightly fuzzy white dot. But time series observations are gold in astronomy. By watching how the comet's brightness changes over hours and days, how its coma expands or contracts, how its position shifts, astronomers can infer rotation rates, activity, variations, and precise trajectory information. The ESA team noted they were surprised by how clearly visible the comet was. They had been unsure whether CASIS designed to photograph Mars from close range would even be able to detect such a faint, distant target. Mars Express, ESA's veteran orbiter that's been studying Mars since 2003, also turned its instruments toward 3IATLAS. The high-resolution stereo camera captured images in multiple color bands, providing information about how the comet's reflectance changes with wavelength. These multi-band observations help constrain the dust properties' particle sizes, composition porosity. Dust in cometary comas isn't uniform. It's a mix of fine grains, larger pebbles, fluffy aggregates, and compacted chunks. How this mix scatters sunlight depends on particle size distribution, which in turn tells us about the sublimation process and how dust is liberated from the nucleus. Now, let's journey to Earth orbit, where an array of space telescopes contributed observations. The Hubble Space Telescope, humanity's most famous observatory, captured images of 3IATLAS on July 21, 2025, when the comet was 277 million miles from Earth. Hubble's image revealed a teardrop-shaped cocoon of dust streaming from the nucleus. Because Hubble was tracking the moving comet, keeping it centered in the frame, the background stars appear as streaks, a reminder that the comet is traveling at enormous speed relative to the stellar background. Hubble's observations through August helped establish the upper limit on the nucleus size at 3.5 miles and the lower limit at 1,400 feet. By measuring how quickly the comet's brightness decreased with distance from the nucleus, researchers could estimate the size of the solid core. The James Webb Space Telescope, the most powerful infrared observatory ever built, observed 3IATLAS in August 2025. Webb's infrared capabilities are perfect for studying comets because many molecular species have strong emissions features in the infrared. The observations that revealed the extraordinary 8:1 CO2 to H2O ratio came from Webb's near-infrared spectrograph. This instrument splits incoming light into a spectrum spanning wavelengths from about 0.6 to 5 micrometers beyond what human eyes can see, but perfect for detecting the vibrational transitions of molecules like carbon dioxide, water, carbon monoxide, and methane. Each molecule has a unique spectral fingerprint, a pattern of absorption or emission lines that identifies it as unmistakably as a barcode identifies a product. Webb is scheduled to observe 3IATLAS again in December 2025. Post-perihelion, to study how the chemistry evolves. Has the CO2 to H2O ratio changed? Are new molecules appearing as deeper layers of ice are exposed? Is there any evidence of complex organics, the kinds of carbon-based molecules that might be precursors to biological chemistry? These observations will happen around the time of closest Earth approach, maximizing the signal strength and data quality. SphereX, the spectrophotometer for the history of the universe. Epoch of Rionization and ICE's Explorer is a relatively new mission that launched in February 2025. Its primary goal is to create an all-sky map in infrared wavelengths, studying billions of galaxies to understand cosmic structure. But in August 2025, SphereX turned its instruments toward 3IATLAS. The mission confirmed strong water ice absorption features and detected an extended carbon dioxide coma, the cloud of CO2 gas surrounding the nucleus. Sphere-X's wide-field capability means it can capture the full extent of the coma in a single observation, something narrower field instruments like Webb can't easily do. NASA's TESS, the Transiting Exoplanet Survey satellite, had serendipitously observed 3IATLAS in May and early June, before anyone knew it was there. TESS is designed to stare at large patches of sky for weeks at a time, looking for the tiny brightness dips that occur when an exoplanet transits in front of its host star. The comet just happened to drift through one of TESS's target fields. When astronomers later searched the archives, they found dozens of images showing 3IATLAS as a faint moving object. These pre-discovery observations extended the observation arc backward by weeks, improving orbit calculations and revealing that the comet was already active when it was beyond 6 AU. Now let's talk about the solar observatories, because they played a crucial role during a period when ground-based telescopes couldn't observe the comet at all. As 3IATLAS approached perihelion in late October, it moved into solar conjunction angularly close to the Sun as seen from Earth. Observing anything near the Sun during the day is nearly impossible from the ground. The sky is too bright, the atmospheric turbulence too severe. But several spacecraft are specifically designed to observe the Sun and its immediate surroundings. NASA's Stereo Solar Terrestrial Relations Observatory consists of 2 spacecraft in solar orbit, one ahead of Earth and one behind, providing stereo views of the Sun. Stereo's heliospheric imagers can photograph regions near the Sun that would be invisible to Earth-based telescopes. From September 11th to October 2nd, Stereo captured images showing 3IATLAS moving through its field of view. The comet appeared against the background of the solar corona and the zodiacal light sunlight scattered by interplanetary dust. These observations showed that the comet's tail was developing beautifully, streaming outward under the pressure of sunlight and the solar wind. SOHO, the Solar and Heliospheric Observatory, a joint ESA-NASA mission, has been continuously observing the Sun since 1995. Its LASCO coronagraphs block out the bright solar disk, allowing observation of the faint corona and objects passing near the Sun. From October 15th to 26th, SOHO tracked 3IATLAS as it rounded perihelion. The images captured during this period are remarkable. The comet's tail stretching across millions of kilometers, plasma structures in the solar corona Earth, visible as a tiny dot in the distance. SOHO has discovered more than 4,000 comets over its nearly 3 decades of operation, so-called sun-grazing comets, that pass extremely close to the Sun, many of which evaporate completely. But this was the first time SOHO purposefully observed an interstellar object. NASA's PUNCH mission, Polarimeter to Unify the Corona and Heliosphere, launched in early 2025 specifically to study how the Sun's corona transitions into the solar wind. PUNCH consists of 4 satellites flying in formation, imaging the Sun's outer atmosphere from multiple angles. In late September and early October, PUNCH captured stunning images of 3IATLAS showing not just the comet, but also the structure of the solar wind streaming past it. These observations are scientifically valuable because they reveal how interstellar material interacts with the solar wind, how the comet's coma is buffeted by charged particles flowing from the Sun, how the tail develops and responds to variations in solar wind pressure. ESA's JUICE mission, currently en route to Jupiter, made observations in November 2025. JUICE carries 11 scientific instruments, including cameras, spectrometers, radar, magnetometers, and particle detectors. Most of these aren't optimized for observing distant comets, but the cameras and spectrometers could be pointed at 3IATLAS to capture data. The JUICE team reported being surprised by how clearly visible the comet appeared in their images, with the coma and signs of activity evident even from JUICE's vantage point more than 100 million miles away. Ground-based observatories made enormous contributions as well. The Very Large Telescope in Chile, actually an array of 4 8.2-meter telescopes that can work together or independently conducted spectroscopic observations throughout the comet's apparition. VLT's high-resolution spectrographs detected the unusual nickel-to-iron ratio we discussed earlier, along with numerous other molecular species. The Nordic Optical Telescope on La Palma, the Southern African Large Telescope in South Africa, the Gemini telescopes in Hawaii and Chile, the Subaru telescope in Hawaii, all contributed observations at different wavelengths and different times, building up a comprehensive data set, spanning the comet's inbound approach, perihelion passage, and outbound departure. Amateur astronomers played a vital role through the Unistellar Network, a global collaboration of citizen scientists using smart telescopes equipped with electronic eyepieces and image stacking capabilities. These telescopes have apertures of just 3 to 4.5 inches, modest by astronomical standards, yet by stacking multiple short exposures and tracking the comet's motion, they achieve sufficient sensitivity to detect 3IATLAS and monitor its brightness. The Unistellar Network contributed hundreds of observations, particularly during periods when professional observatories were clouded out or focused on other targets. This citizen science component democratizes astronomy, allowing anyone with modest equipment and clear skies to contribute meaningful data to cutting-edge research. Think about what this observation campaign represents. We're talking about assets worth billions of dollars, mission timelines planned years in advance, observation schedules carefully orchestrated, all being flexibly adjusted to capture data about an object that was discovered just months ago. This kind of rapid response wasn't possible even a decade ago. The communication infrastructure didn't exist. The coordination mechanisms weren't in place, and we simply had fewer spacecraft scattered through the solar system. The data flowing from all these observations is staggering in volume. Each instrument produces different types of data, images in various wavelengths, spectra covering different spectral ranges, time series, brightness measurements, polarimetry, data, positional astrometry. All of this must be calibrated, processed, analyzed, cross-compared. Teams of researchers worldwide are working with these data sets, writing papers, building models, testing hypotheses. The scientific output from 3IATLAS will continue for years as researchers mine the data for insights. But there's also a learning component here. Every observation campaign teaches us how to do the next one better. What worked well? What challenges did we face? How quickly can we mobilize resources? What kinds of observations provide the most valuable data? These lessons are being cataloged and will inform future rapid response campaigns for the next interstellar visitor. ESA's Comet Interceptor mission, scheduled to launch in 2029, is specifically designed to wait in space for a suitable target, ideally a pristine comet from the Oort cloud, or, though unlikely, an interstellar object like 3IATLAS. Comet Interceptor will consist of 3 spacecraft that can separate and observe the target from multiple angles during a high-speed flyby. The mission design is informed by what we learned from Oumuamua and 2I Borisov, and now from 3IATLAS. We know what kinds of measurements are most valuable. We know what instruments to include. We know how to coordinate multi-spacecraft observations. The observation campaign for 3IATLAS also highlights the value of international cooperation. NASA, ESA, JAXA, the Chinese National Space Administration, private observatories, amateur astronomers, all contributing to a shared goal. There are no national boundaries in space, no borders drawn across the solar system. when an interstellar object passes through it belongs to all of us. The data is shared openly, published in scientific journals, accessible worldwide, discussed at international conferences. This is science at its best, collaborative, transparent, driven by curiosity rather than competition. Have you ever wondered how scientists from different countries, different institutions, different backgrounds manage to coordinate so effectively? It's a testament to the shared language of science, mathematics, physics, chemistry, and the common protocols that have been developed over decades. When an astronomer in Chile emails a colleague in Hawaii with spectroscopic data, they both understand exactly what the numbers mean, how the data was acquired, what calibrations were applied. This shared understanding enables collaboration on a global scale, but coordination is only part of the story. The real magic happens in the analysis when researchers start comparing observations from different platforms, looking for patterns, testing ideas, building models that can explain what we're seeing. And one particular moment stands out in this whole campaign, one date when Earth had its closest and best view of this ancient messenger from the stars, when professional and amateur observers alike turned their instruments skyward to document a historic encounter that will never happen again in our lifetimes. That date, December 19th, 2025, represents more than just a geometric milestone. It represents humanity's collective opportunity to bear witness to something extraordinary, something that connects us to the broader universe in profound ways. There are certain dates that become inscribed in the collective memory of humanity, days when something extraordinary occurred, when we witnessed events that changed our understanding of the world. December 19th, 2025 may not carry the dramatic weight of a moon landing or the discovery of a new planet, but for those who understand what's happening in the heavens that day, it represents something profound. The moment when an object from another star system passes at its closest point to Earth, when we have our optimal window to study chemistry and physics from a world we'll never visit. At 1.798 astronomical units, 167 million miles, 3IATLAS will be near enough for dedicated observers with modest telescopes to see it far enough that there's absolutely no danger and positioned perfectly in the night sky for documentation. This is our moment. After December 19th, the comet will fade as it recedes, slipping beyond the reach of all but the most powerful instruments, eventually vanishing into the cosmic darkness from which it came. This is the night when amateur astronomers and professionals alike will train their instruments on a visitor that has traveled for millions of years to arrive here now for this brief encounter that will never be repeated. If this moment resonates with you, if you feel the significance of bearing witness to something so rare, I'd be honored if you'd like this video and join our community by subscribing. We're here to explore these cosmic mysteries together, whether you're wide awake under the stars or drifting peacefully into sleep. Let's start with what December 19th actually means in practical terms. At closest approach, 3IATLAS will be 1.798 astronomical units from Earth. Let's unpack that measurement. 1 astronomical unit is the average distance between Earth and the Sun, about 93 million miles or 150 million kilometers. So, 1.798 AU is roughly 167 million miles or 269 million kilometers. To give you perspective, Mars at its closest approach to Earth is about 35 million miles, meaning 3IATLAS at closest approach is still nearly 5 times farther than Mars at its nearest. The Moon, by comparison, is only 240,000 miles away, about 700 times closer than 3IATLAS will be. So, when we say closest approach, we're talking about cosmic scales, not anything resembling proximity in human terms. This distance is perfectly safe. There's no possibility of collision, no gravitational effects on Earth, no disruption to our orbit or our satellite systems. The comet poses zero threat. In fact, planetary defense experts view 3IATLAS as an excellent training opportunity, a chance to practice orbit determination, international data sharing and crisis communication protocols without any actual crisis. Real interstellar objects passing through give us valuable experience for the unlikely but theoretically possible scenario of an interstellar object on a collision course. We're building institutional knowledge, refining our methods, learning how to track these visitors with ever greater precision. But the distance also presents challenges for observation. At magnitude 10 to 11, 3IATLAS is not visible to the naked eye. You won't look up on December 19th and see a bright comet stretching across the sky like Hale-Bopp in 1997 or Neowise in 2020. This is a telescopic object requiring optical aid to detect. Amateur astronomers with telescopes in the 6 to 8-inch aperture range, fairly standard equipment for serious hobbyists, should be able to see it as a faint, fuzzy patch of light under dark skies. Larger telescopes with apertures of 10 inches or more will reveal more detail, perhaps a hint of the coma structure, maybe the beginning of the tail, extending away from the nucleus. Astrophotographers have been planning their imaging sessions for weeks. Capturing a good image of a faint comet requires patience and skill. You need dark skies far from city lights. You need a telescope with accurate tracking, a motorized mount that can follow the sky's rotation, keeping the comet centered in the field of view during long exposures. You need a sensitive camera, often a cooled CCD or CMOS sensor that can accumulate photons over minutes without excessive noise. And you need to know exactly where to point, because the comet won't be obvious in the viewfinder. You're searching for a specific faint smudge in a specific location among thousands of stars. The comet's position on December 19th is near the constellation Leo, close to the bright star Regulus. Leo is a prominent constellation in the winter sky, shaped like a lion, with Regulus marking the lion's heart. For observers in the northern hemisphere, Leo rises in the east after midnight in mid-December and climbs higher through the pre-dawn hours. This means prime observing time is in the early morning of December 19th, between about 2 a.m. and 6 a.m. local time, when Leo is well placed and the sky is dark. For southern hemisphere observers, Leo is visible but lower in the northern sky, making observations somewhat more challenging due to atmospheric thickness and lower elevation angles. Finding the comet requires precise coordinates, right ascension and declination, the celestial equivalent of longitude and latitude. These coordinates change daily as the comet moves against the background stars. Astronomy software and star charts provide updated positions, allowing observers to point their telescopes accurately. Some modern telescopes have computerized go-to mounts that can automatically slew to entered coordinates, making the search much easier. Others require manual star hopping, finding a recognizable pattern of stars near the target location, and then carefully panning the telescope to the precise spot. Once located, what will observers see? The nucleus itself is far too small to resolve. Remember, it's somewhere between 440 meters and 5.6 kilometers across, and at 167 million miles distance, even the larger size estimate subtends an angle of only about 0.07 arcseconds. For comparison, the theoretical resolution limit of an 8-inch telescope is around 0.5 arcseconds. And atmospheric turbulence typically limits practical resolution to 1 or 2 arcseconds. So, the nucleus appears point-like indistinguishable from a star. What makes it identifiable as a comet is the coma, the diffuse cloud of gas and dust surrounding the nucleus. The coma might extend several arc-minutes across, depending on activity level and how you define the boundary. Within that fuzzy glow, the nucleus sits at the center, the brightest point, but still unresolved. The tail, if visible, will extend away from the sun's direction. Comet tails always point roughly away from the sun because they're driven by solar radiation pressure and the solar wind. The dust tail, made of solid particles reflecting sunlight, appears yellowish or whitish and curves slightly following the comet's orbital path. The ion tail, made of ionized gas swept away by the solar wind, appears bluish in color, images and points more directly away from the sun, sometimes stretching for enormous distances. For 3IATLAS, the tail structure in December will be less prominent than it was at perihelion. The comet is now moving away from the sun. Activity is declining, and the production of new dust and gas is decreasing. But observers with sensitive equipment and dark skies should still be able to detect the tail extending perhaps several degrees across the sky. Professional observatories are maximizing their time around December 19th. The James Webb Space Telescope has scheduled observations to capture near-infrared and mid-infrared spectra, studying how the comet's molecular emissions have evolved since the August observations. Are the volatile ices still sublimating at high rates, or has activity dropped sharply? How has the CO2 to H2O ratio changed? Are there any surprises, unexpected molecular species, unusual emission, feature signs of compositional heterogeneity? As different regions of the nucleus are exposed, ground-based observatories with large apertures and sophisticated instruments are conducting complementary observations. The Keck telescopes in Hawaii, with their 10-meter mirrors, can gather enough light to perform detailed spectroscopy even on faint objects. The Subaru telescope, also in Hawaii, with an 8.2-meter mirror, excels at wide-field imaging, capable of capturing the full extent of the coma and tail in a single exposure. The Very Large telescope in Chile, with its array of 8 2-meter mirrors, can combine light from multiple telescopes to achieve higher resolution through interferometry. Though this technique is challenging for moving targets like comets, radio observatories are contributing as well. The Atacama Large Millimeter, Submillimeter Array ALMA in Chile can detect molecular emission lines at millimeter wavelengths. Molecules like methanol, formaldehyde, hydrogen cyanide, and carbon monoxide have strong transitions at these wavelengths. ALMA observations can measure production rates for these molecules, providing a census of the comet's volatile inventory. The data from ALMA complements optical and infrared observations, filling in gaps in our understanding of the comet's chemistry. One of the fascinating aspects of December 19th is that it's a global event. While the optimal viewing is during local nighttime when Leo is above the horizon, the comet doesn't disappear when the sun rises. Spacecraft and space telescope can observe continuously unaffected by Earth's day-night cycle. The Hubble Space Telescope will capture images adding to the data set that began in July. Hubble's sharp optics and well-calibrated instruments provide a consistent standard for measuring brightness and coma size, allowing comparisons across months of evolution. For citizen scientists using the Unistellar network, December 19th represents a coordinated observing campaign. Dozens of observers across multiple continents will capture images throughout the night, creating a time series data set that tracks brightness variations over hours. These variations can reveal rotation effects as different regions of the nucleus come into and out of sunlight. The overall brightness fluctuates. By analyzing the timing and amplitude of these fluctuations, researchers can refine estimates of the rotation period and infer something about the nucleus shape and surface properties. There's something poignant about the collective effort to observe on this particular night. In a world often divided by politic, culture, and geography, we have thousands of people united by curiosity, all looking at the same patch of sky, documenting the same distant object. A comet from another star system becomes a focal point for human cooperation and shared wonder. Whether you're observing from a professional observatory in Chile, an amateur telescope in your backyard in Ohio, or watching a live stream from your phone in Tokyo, you're participating in a moment of collective discovery. But let's talk about what December 19th means scientifically. Why is closest approach significant beyond just being a milestone date? The primary reason is signal strength. In astronomy, distance matters enormously. The brightness of an object falls off with the square of the distance double the distance, and the object appears 4 times fainter. At closest approach, we receive maximum flux from the comet, meaning our instruments can achieve the highest signal-to-noise ratios. Higher signal-to-noise means we can detect fainter spectral features, measure weaker emissions, resolve finer details in the coma structure. After December 19th, as the comet recedes, all of these measurements become progressively harder. There's also a geometric factor. The angle between the Sun, the comet, and Earth affects what we see. This angle is called the phase angle. At small phase angles, when we're looking at the sunlit side of the comet nearly head-on, we see maximum brightness because dust and ice particles scatter sunlight, preferentially in the forward direction. As the phase angle increases, brightness decreases. On December 19th, the geometry is favorable. We're viewing the comet at a moderate phase angle that balances brightness with visibility. Too close to zero phase angle and the comet is angularly near the Sun in our sky, making observation difficult. Too large a phase angle and the comet is faint and shadowed. December the 19th hits a sweet spot. After this date, 3IATLAS begins its long fade into obscurity. By late December, it will have dimmed to magnitude 12 or 13, requiring telescopes with at least 10 to 12-inch apertures to detect. By January 2026, magnitude 14 or fainter accessible only to dedicated amateurs with large scopes and dark skies or professional facilities. By February, magnitude 16 or beyond, essentially requiring professional observatories with large apertures and sensitive instruments. By mid-2026, as the comet passes Jupiter and continues outward, it will be magnitude 18 or fainter detectable only by major research telescopes. And eventually, by the late 2020s or early 2030s, it will fade beyond magnitude 24 or 25, becoming lost among the billions of faint background galaxies that populate deep sky images. This fade is inevitable and irreversible. Unlike some comets that return to the inner solar system on periodic orbits, giving us multiple opportunities to study them. 3IATLAS makes only one pass. We get one chance, and that chance is now peaking on December 19th. Future generations will not see this comet. They'll study the data we collect, read the papers we publish, view the images we capture, but they will never observe 3IATLAS directly. This puts a certain responsibility on the current generation of astronomers, amateur and professional alike. The data we gather now is all the data that will ever exist for this object. We have to get it right. Interestingly, there's been some public confusion because another comet designated C2025K1 Atlas was discovered earlier in 2025 by the same Atlas survey. This second comet is not interstellar, it's a conventional solar system comet that recently fragmented after a close pass by the Sun. Some media outlets and social media posts have conflated the two objects, creating mix-ups about which comet is which. It's worth noting, 3IATLAS, the interstellar visitor, is not. Fragmenting is not in danger of disintegrating and has shown no signs of breakup. The similarity in naming both discovered by Atlas, both reported in 2025, is purely coincidental, but has led to some confusion that astronomers have worked to clarify. On the night of December 19th, some observers might wonder, what am I actually looking at? When you see that faint fuzzy glow through your telescope, you're seeing light that left the comet just 14 minutes ago. The light travel time from 167 million miles. But the comet itself, the ice and dust you're seeing, is billions of years old. The molecules sublimating off the nucleus were incorporated into the comet when it formed in a protoplanetary disk around another star, perhaps 10 billion years ago, when the universe was less than a third its current age. Those molecules have been frozen preserved, traveling through the interstellar void for countless millennia. Now, briefly warmed by our sun, they're evaporating into space, creating the display you're witnessing. It's a profound connection across space and time. Have you ever thought about how lucky we are to live in this particular era? A century ago, We didn't have the telescopes, the sensors, or the understanding to recognize interstellar objects. A century from now, we'll likely have better technology, but we won't have 3IATLAS. We have this narrow window, December 2025, this year, this month, this week, when a visitor from another star system is within range of our instruments. And you're alive to know about it, to observe it, if you choose to understand what it represents. That's extraordinary. December 19th is also notable for outreach and public engagement. Observatories around the world are hosting public viewing events, live streaming telescope, feeds offering talks and Q&A sessions. Planetariums are creating special programs about interstellar visitors. Science museums are setting up displays. The goal is to share this rare event with as many people as possible to inspire wonder, to remind everyone that we live in a universe far stranger and more magnificent than everyday life might suggest. These outreach efforts plant seeds. Perhaps a child attending a viewing event becomes the astronomer who studies the next interstellar visitor, or the engineer who designs the spacecraft that finally intercepts one. But while December 19th marks the closest approach and the optimal observation window, it's not the end of the story. The data collected on this night and in the days surrounding it will be analyzed for months and years. Researchers will compare brightness measurements across multiple observatories to look for short-term variability, outbursts, rotational brightness changes, effects of changing solar illumination geometry. They'll combine spectra from different instruments to build a complete picture of the comet's molecular inventory. They'll model the coma structure, tracking how dust moves away from the nucleus under the combined influence of solar radiation's pressure and the nucleus's weak gravity. And beyond the immediate scientific analysis, there's a larger question. What does 3IATLAS teach us about the galaxy we inhabit? About the diversity of planetary systems, about the processes that eject comets from their home systems and send them wandering through the void, about the longevity and preservation of primordial ices over billions of years. These questions don't have simple answers. They require synthesizing data from 3IATLAS with data from other interstellar objects, from exoplanet observations, from studies of our own solar system's comets. The full significance of 3IATLAS will only become clear as we place it in the broader context of galactic astronomy and planetary science, a process that's just beginning. We've now studied 3 interstellar objects: Oumuamua in 2017, 2I, Borisov in 2019, and 3IATLAS in 2025. 3 visitors from beyond our solar system, 3 completely different objects, 3 radically distinct stories. Oumuamua arrived like a mystery, wrapped in an enigma, elongated, possibly tumbling, showing strange acceleration, with no visible outgassing departing, before we could truly understand what it was. 2I Borisov behaved like a well-mannered guest, displaying conventional comet activity rich in carbon monoxide, but otherwise familiar, teaching us that some interstellar comets resemble our own. And now, 3IATLAS Extreme in its chemistry, unpredictable in its activity, challenging every model we tried to apply to it. Each interstellar visitor has been weird in a different way, and collectively they're teaching us a profound lesson. The universe is far more diverse than our single solar system ever suggested. Every star system has its own story, its own chemistry, its own population of small bodies shaped by unique conditions. We're only beginning to understand. If these lessons resonate with you, if you're realizing just how vast and varied the cosmos truly is, I'd be grateful for your like. And subscribing means we can continue exploring these cosmic mysteries together as new discoveries unfold. Your presence here, whether awake or drifting peacefully towards sleep, is what makes this journey meaningful. Let's start by examining what makes each interstellar visitor unique, because the contrasts are striking. Oumuamua, officially designated 1I 2017 U1, was discovered on October 19, 2017 by the Pan-STARRS telescope in Hawaii. The name means scout or messenger in Hawaiian fitting for the first confirmed interstellar object ever detected. From the beginning, Oumuamua was puzzling. Its light curve, the variation in brightness as it tumbled through space, suggested an extremely elongated shape, perhaps 10 times longer than it was wide. Think of a cigar or a cucumber spinning end over end. No object in our solar system has quite that geometry, though some asteroids come close. More puzzling still was its motion. As astronomers tracked Oumuamua's trajectory, they noticed it was accelerating slightly away from the sun, faster than gravity alone could explain. This non-gravitational acceleration resembled what comets display when outgassing creates thrust. But Oumuamua showed no visible coma, no tail, no evidence of sublimating ice. Sensitive searches for gas emissions came up empty. It appeared dry, inert like an asteroid rather than a comet. Yet something was pushing it. Harvard astronomer Avi Loeb famously proposed that Oumuamua might be artificial, perhaps a solar sail from another civilization. This hypothesis generated enormous media attention and spirited debate, with most astronomers favoring natural explanations involving exotic ices or unusual surface properties. To this day, we don't have a definitive answer. Oumuamua sped away, fading beyond detection within months, leaving behind more questions than answers. 2I Borisov was refreshingly straightforward by comparison. Discovered on August 30th, 2019 by amateur astronomer Gennady Borisov in Crimea, this comet displayed classic cometary behavior from the start. It had a bright coma, a visible tail, and strong emission features indicating active sublimation of ice. Spectroscopic studies revealed it was extraordinarily rich in carbon monoxide. The CO to H2O ratio was around 2:1, making it one of the most CO-dominated comets ever observed. This suggested Borisov formed in an extremely cold region of its parent star system, where CO ice could condense and remain stable. But aside from this compositional peculiarity, Borisov behaved much like solar system comets from the Oort cloud, those pristine long-period comets that have been barely altered since their formation 4.6 billion years ago. The predictability of Borisov was scientifically valuable because it suggested that comets across the galaxy might follow similar physical laws and evolutionary pathways. If interstellar comets are just like solar system comets, but with slightly different compositions that simplifies our understanding, we can apply existing models, make reasonable predictions, extrapolate from what we know. Borisov gave astronomers confidence that the comet physics developed over decades of studying solar system objects would translate well to interstellar visitors. And then came 3IATLAS, shattering that confidence. Nothing about 3IATLAS is straightforward. The 8:1 CO2 to H2O ratio is unprecedented, not just unusual, but off the charts compared to any comet previously studied. The early onset activity at 6.4 AU, when water ice should be dormant and even CO2 should be barely active, violated expectations. The brightness surge in September exceeded model predictions. The unusually high nickel-to-iron ratio in gaseous emissions suggested either exotic formation conditions or selective release mechanisms we don't understand. The comet's behavior has been consistently unpredictable, forcing astronomers to revise their models multiple times. What do these three objects tell us collectively? First, and most importantly, they demonstrate extreme diversity. If we had only seen Oumuamua, we might have concluded that interstellar objects are predominantly dry, rocky bodies, asteroids rather than comets. If we'd only seen Borisov, we might have assumed interstellar comets are compositionally similar to solar system comets, just with variations in volatile ratios. But now, with 3IATLAS in the mix, we know the truth is far more complex. Interstellar objects span a wide range of properties, compositions, and behaviors. There's no single typical interstellar object, just as there's no single typical planet or star. This diversity shouldn't surprise us, yet it does. Human psychology tends toward pattern recognition and generalization. We see a few examples and unconsciously assume they're representative. But the universe doesn't care about our psychological biases. Nature explores every possible configuration allowed by physics and chemistry. If a type of object can exist, if the laws of nature permit its formation and survival, then somewhere in the galaxy it probably exists. Our job as scientists is to observe, document, and try to understand the full range of possibilities. The age implications of 3IATLAS add another layer to this lesson. If the comet truly is 7 to 14 billion years old, it predates our solar system by billions of years. It formed when the Milky Way was younger, when the galactic chemical composition was different, when the rate of star formation was higher. The thick disk population of stars, older metal poor, born earlier in galactic history, produced planetary systems with different elemental ratios than the younger metal-rich systems like ours. A comet forming around a thick disk star 10 billion years ago would incorporate whatever elements were available at that time and place. The carbon-to-oxygen ratio, the abundances of nitrogen and sulfur, the availability of heavy elements like nickel and iron, all of these would differ from what we see in solar system comets formed 4.6 billion years ago from the solar nebula. This means 3IATLAS is not just a messenger from another star system. It's a messenger from another epoch of galactic evolution. It carries information about conditions that existed when the universe was less than a third its current age, when entire classes of stars and planets that exist today hadn't yet formed. Studying its composition is like reading a message written billions of years ago, preserved in ice, finally delivered to our doorstep. The ejection mechanisms that send objects into interstellar space also reveal something fundamental about planetary system dynamics. In our solar system, Jupiter is the great ejector. Its immense gravity has flung countless comets and asteroids into interstellar space over the past 4.6 billion years. Every close gravitational encounter between a small body and Jupiter is a game of chance. Sometimes the object is deflected into the inner solar system, sometimes into a more distant orbit, and sometimes it gains enough velocity to escape the sun's gravity, entirely becoming interstellar. Computer simulations suggest our solar system has ejected far more mass into interstellar space than currently remains in the asteroid belt and Kuiper belt combined. We've been prolific exporters of material. Other star systems presumably do the same. Any system with a Jupiter-like planet, a massive world, and a relatively close orbit will eject small bodies over time. In fact, systems with multiple giant planets may be even more efficient at ejection because the planet's gravitational influences can interact, creating regions of orbital instability where small bodies are quickly scattered outward. This means the interstellar medium, the space between stars, is filled with ejected comets, asteroids, and planetary debris. These objects vastly outnumber the stars themselves. For every star in the galaxy, there might be trillions of interstellar objects drifting through the void. The statistics are staggering when you think about it. The Milky Way contains roughly 200 to 400 billion stars. If each star system ejects even a modest amount of material, say a few Earth masses worth of comets and asteroids, over its lifetime, the total mass in interstellar objects could equal or exceed the mass in all the planets in all the star systems in the galaxy. We're swimming in a sea of interstellar debris, most of it too small and too distant to detect, but occasionally one passes close enough to our sun that we can spot it. Current estimates refined by the discoveries of Oumuamua Borisov and 3IATLAS suggest there might be one interstellar object larger than about 100 meters passing within Jupiter's orbit at any given time. Smaller objects, meter-sized or smaller, probably number in the thousands within the same volume. But detecting them is incredibly difficult. They're faint, fast-moving, and unpredictable. We discover them only through systematic sky surveys that photograph large areas, repeatedly looking for anything that moves against the stellar background. This brings us to the Vera Rubin Observatory, which represents a quantum leap in our ability to detect these visitors. Scheduled to begin full operations in 2025, the Rubin Observatory will photograph the entire visible sky every few nights using the largest digital camera ever built for astronomy, 3.2 gigapixels. Each image will cover an area of sky equal to 40 full moons. Over the course of its planned 10-year survey, Rubin will generate an unprecedented database of moving objects, asteroids, comets, trans-Neptunian objects, and yes, interstellar visitors. Projections suggest Rubin might detect anywhere from a few dozen to potentially hundreds of interstellar objects over its operational lifetime. That's a radical shift from the current situation, where we've detected only 3. With dozens of examples, we can start doing statistical studies. What's the size distribution? How common are comets versus asteroids? Do objects from certain galactic directions have different compositions, perhaps reflecting the chemical properties of different regions of the galaxy? What fractions show unusual properties like Oumuamua's unexplained acceleration or 3IATLAS's extreme activity? These statistical questions can't be answered with a sample size of 3. We need larger numbers to distinguish between rare outliers and common archetypes. Every interstellar object we detect refines our understanding of the underlying population. It's like trying to understand human diversity by meeting just 3 people. You'll get 3 unique individuals, but you won't understand the full range of human variation until you've met thousands. The same principle applies to interstellar objects. The discovery of 3IATLAS also has implications for planetary defense, the effort to detect and track objects that might pose collision threats to Earth. While 3IATLAS itself poses no danger, its trajectory demonstrates how quickly an object on a hyperbolic path can sweep through the inner solar system. From discovery in early July to perihelion in late October was less than 4 months. If a similar object were on a collision course with Earth, we'd have very limited time to respond. Current planetary defense strategies assume we'll have years or decades of warning for most threats based on typical near-Earth asteroids with elliptical orbits that return periodically. An interstellar impactor would give us only months at most, possibly just weeks if we're unlucky with the discovery geometry. This scenario is extremely unlikely. The odds of an interstellar object hitting Earth are vanishingly small, much lower than the already small risk from solar system asteroids. But it's not zero, and 3IATLAS serves as a useful test case. How quickly can we determine a newly discovered object's trajectory? How fast can we mobilize international resources to improve orbit predictions? How do we communicate uncertain but potentially serious risks to the public? These questions are easier to address when there's no actual danger, when we're dealing with 3IATLAS passing safely at 1.8 AU rather than an impactor weeks away from collision. The scientific return from 3IATLAS also highlights the value of multi-wavelength, multi-platform observations. No single telescope or instrument could have characterized this comet comprehensively. We needed optical observations to measure brightness and rotation infrared spectroscopy, to identify molecular species, ultraviolet observations, to map the hydrogen cloud, radio observations to detect complex organic spacecraft at Mars, to provide close-up views, space telescopes to capture data when ground-based telescopes couldn't. Each contributed a piece of the puzzle. Only by combining all these pieces can we build a complete picture. This integrated approach is becoming standard in modern astronomy, but it requires coordination that would have been impossible even a generation ago. The internet enables instant communication between observatories worldwide. Standardized data formats allow observations from different facilities to be combined seamlessly. Open data policies mean that researchers can access observations made by others, multiplying the scientific value. The study of 3IATLAS is a triumph of collaborative, open international science. But beyond the technical and scientific lessons, there's something more philosophical that 3IATLAS teaches us: humility. Every time we think we understand how comets work, how planetary systems form, how objects behave as they move through space, nature presents us with something that doesn't fit our models. Oumuamua didn't fit. 3IATLAS doesn't fit. This is actually healthy for science. It means we're pushing the boundaries of knowledge, encountering phenomena at the edge of our understanding. If every new discovery perfectly matched predictions, we wouldn't be learning anything new. We'd just be confirming what we already knew. The surprises keep us honest. They prevent us from becoming overconfident in theories that might be correct for familiar situations, but break down under unusual conditions. They force us to think more deeply about underlying physics, to question assumptions, to consider alternative explanations we might have dismissed too quickly. 3IATLAS's extreme CO2 dominance challenges models of how volatiles are distributed in protoplanetary disks. Its early activity suggests sublimation processes can operate under conditions we thought impossible. Its unusual metal ratios hint at nucleosynthetic variations across the galaxy. Each of these challenges makes our models better by forcing us to account for a wider range of phenomena. There's also an emotional dimension to these discoveries that's worth acknowledging. When astronomers saw Oumuamua accelerating without visible outgassing, there was genuine bewilderment. When Borisov appeared and behaved normally, there was relief. Okay, interstellar comets can be normal. And when 3IATLAS started exceeding expectations and showing unprecedented chemistry, there was renewed excitement tinged with frustration. Excitement because it's teaching us something new. Frustration because it's not easy to understand. These emotional responses are part of the scientific process, part of what makes research deeply human rather than coldly mechanical. And what about the broader implications for life in the universe? If comets delivered organic molecules to the early Earth, contributing to the chemistry that eventually led to life, and if different star systems produce comets with wildly different compositions, then every planet receives a unique chemical input from cometary impacts. Earth received water-rich, organic-laden comets from our solar system. A planet in 3IATLAS's home system would receive CO2-rich comets with perhaps different organic inventories. How would that affect the potential for life? Would life be more likely, less likely, or simply different? We don't know, and we won't know until we have more examples, more interstellar objects, more exoplanet studies, more understanding of how chemistry evolves in diverse environments. But the question is no longer abstract. We now have concrete evidence that planetary system chemistries vary dramatically. The ingredients available for life differ from system to system. This doesn't change the fundamental question of whether life exists elsewhere. Statistical arguments based on the number of planets still suggest it's likely, but it adds richness to our understanding of what forms that life might take, what biochemistries it might use, what environmental conditions it might require. As we stand at the close of 2025, watching 3IATLAS recede into the distance, we're left with more questions than we started with, but also with deeper insight into the diversity of the cosmos. We've learned that every interstellar visitor brings unique lessons, that our solar system is just one example among billions, that chemistry and physics play out in infinite variations across the galaxy. These lessons aren't just academic. They reshape our cosmic perspective, our understanding of our place in the universe, our appreciation for both the familiarity and the strangeness of the worlds beyond our own. And as 3IATLAS continues its eternal journey, fading from our instruments, but not from our memory, we're compelled to ask, where is it going? What future awaits this ancient wanderer as it returns to the interstellar void? And what does its journey tell us about the nature of time, space, and existence itself in this vast cosmos we're only beginning to understand? Picture the comet 3IATLAS right now at this very moment as you listen to these words moving outward through the solar system at over 150,000 miles per hour. It has passed its closest approach to Earth. The geometry that brought us together, this ancient traveler from another star system and our pale blue world, is already shifting. Distance grows, the comet dims, the window closes. But the journey continues as it has for billions of years, as it will for billions more. Where is it going? The answer is both simple and profound, everywhere and nowhere. 3IATLAS is leaving our solar system, heading in the direction of the constellation Telescopium in the southern sky. But Telescopium isn't a destination, it's just a direction, a line drawn across the galactic map. The comet will take millions of years to travel even a single light year. At its current velocity of roughly 57 kilometers per second, relative to the Sun about 35 miles per second, 3IATLAS needs approximately 20,000 years to cover 1 light year of distance. The nearest star to our Sun, Proxima Centauri, is 4.24 light years away. Simple arithmetic, it would take 3IATLAS roughly 85,000 years to reach Proxima if it were headed in that direction. But it's not. It's heading elsewhere into a region of space between stars where there may be no stellar encounters for millions of years. Think about what that means. This object has been traveling through the galaxy for so long that entire civilizations could rise and fall in the time it takes to journey from one star to another. When 3IATLAS last passed near a star, its parent star, the one around which it formed 7 to 14 billion years ago, human beings didn't exist. Earth didn't exist. The Sun didn't exist. The Milky Way was younger, smaller, more chaotic. And now, having briefly warmed itself in our Sun's light, having briefly allowed us to study it, having briefly connected two stellar systems separated by unimaginable distance and time, it returns to the cold. The temperature in interstellar space hovers just a few degrees above absolute zero, around 2.7 Kelvin. The temperature of the cosmic microwave background radiation left over from the Big Bang. 3IATLAS will cool as it recedes from the Sun. The surface, which reached perhaps 200 Kelvin at perihelion, warm enough to drive vigorous sublimation, will drop back below 100 Kelvin within months, below 50 Kelvin within a few years, eventually settling back toward that ambient 3 Kelvin of the interstellar medium. At those temperatures, even the most volatile ices cease activity. Carbon monoxide, the most volatile component, might still very slowly sublime at 10 or 20 Kelvin over geological time scales, but the rate becomes negligible. The comet goes dormant. It becomes once again a frozen relic drifting through the void. But something has changed. 3IATLAS is not the same object that entered our solar system. It has lost mass thousands of tons of ice and dust shed during its months of activity. Its surface has been reshaped. Sublimation carved new pits and valleys. Cliffs collapsed. Fresh ice exposed in some regions, dust mantles built up in others. The nucleus is smaller now, lighter with a slightly different shape and rotation rate than when it arrived. These changes are permanent. The lost material is scattered along its orbital path, gradually dispersing into the interstellar medium, never to be recovered. The comet that leaves is not the comet that came, and it carries with it the invisible mark of our attention. We have photographed it, analyzed its light, measured its trajectory, decoded its chemistry. We know things about 3IATLAS that no other consciousness in the universe likely knows, because we were here now when it passed through. If intelligent beings exist around the star, where it formed, they have no knowledge of where their ejected comet traveled. They don't know it survived for billions of years. They don't know it briefly visited another star system and was studied by curious creatures who pointed telescopes skyward. The comet is a messenger, but it delivers its message only to those it encounters. We received the message. We read what we could. And now the messenger continues on, carrying information about our solar system, traces of solar wind particles embedded in its surface, perhaps microscopic dust grains from our system that collided with the coma toward unknowable future encounters. Let's fast forward through the comet's immediate future the next few years that we can predict with reasonable accuracy. In March 2026, just a few months from now, 3IATLAS will pass Jupiter's orbit at a distance of about 0.358 astronomical units from the giant planet, roughly 33 million miles. This is the comet's last significant planetary encounter. Jupiter's immense gravity, 318 times Earth's mass, will exert a measurable perturbation on the trajectory, slightly deflecting the path. Orbital dynamicists will update their calculations, refining the post-encounter velocity and direction. But Jupiter cannot capture 3IATLAS. The comet is moving far too fast with far too much energy to be bound. The encounter is just a brief gravitational nudge, a cosmic goodbye from the largest planet in our system. By late 2027 or early 2028, 3IATLAS crosses Saturn's orbital distance. By the early 2030s, it reaches Uranus's orbit. By the mid-2030s, Neptune's orbit approximately 30 astronomical units from the Sun, the same distance where it crossed inbound back in early 2024. As it passes this milestone, the comet will have completed its loop through the planetary region of our solar system. Beyond Neptune lies the Kuiper Belt, a region of icy bodies and dwarf planets, extending to perhaps 50 or 60 AU. 3IATLAS will pass through this region in the 2040s and 2050s, though by then it will be so faint, probably magnitude 25 or dimmer, that even the largest telescopes will struggle to detect it. Beyond the Kuiper Belt lies the scattered disk, and farther still, the Oort cloud, a vast spherical shell of comets surrounding the Sun, extending perhaps 100,000 AU into space roughly 2 light years. 3IATLAS will spend thousands of years traversing this region. By the time it finally exits the Oort cloud and returns to true interstellar space, humans may have colonized other planets, or we may be extinct. Civilizations rise and fall on timescales far shorter than a comet's journey. But let's zoom out further. Let's think galactically. 3IATLAS is traveling through the Milky Way at about 60 kilometers per second, relative to the local standard of rest, the average velocity of stars in the solar neighborhood. This is not particularly fast by galactic standards. Stars in the thick disk population, where 3IATLAS likely originated, have similar velocities. The comet follows a galactic orbit just as the Sun does, circling the Milky Way's center, every 200 million years or so, a cosmic year. The Sun has completed roughly 23 galactic orbits since it formed 4.6 billion years ago. If 3IATLAS is 10 billion years old, it has completed perhaps 50 galactic orbits during its lifetime, seeing the galaxy from countless perspectives, witnessing the dance of spiral arms, the births and deaths of star clusters, the slow evolution of galactic structure. Where will it be in a million years? We can't predict with precision too many small gravitational perturbations from passing stars, too much chaotic dynamics. But statistically, we can say it will be roughly 60 light years away from its current position, having traveled at 60 kilometers for a million years. That's still nowhere really in a galaxy, 100,000 light years across. It will likely have passed no closer than a light year or two to any star system during that time, because stars are so far apart. Space is overwhelmingly empty. Will it ever encounter another star system the way it encountered ours? Possibly, but the odds are low. Computer simulations of interstellar object trajectories suggest that once ejected, most objects never have close stellar encounters again. They simply drift through the interstellar medium, indefinitely occasionally passing light years from stars, but never close enough for the star's gravity to significantly perturb them, or for the star's heat to warm them. 3IATLAS could wander the galaxy for the remaining life of the universe tens of billions of years without ever warming up again. Its perihelion passage through our solar system in October 2025 might be the last time it ever experiences solar heating. Or it could get lucky. Perhaps in 50 million years, it passes within a few AU of a star warming, briefly outgassing, creating a temporary coma visible to any observers in that system. Perhaps in 500 million years, it passes close to a red dwarf or a binary star system, creating a more complex gravitational encounter that significantly alters its trajectory. Or perhaps in a billion years, it passes through a dense molecular cloud, a stellar nursery where new stars are forming and get swept up in the formation of a new planetary system, becoming incorporated into that system's comet population, finally finding a new home after eons of wandering. These scenarios are all possible, though. Each is individually unlikely. The universe is vast. Time is long, and probability works in strange ways over cosmic scales. What we can say with confidence is that 3IATLAS will continue existing in some form for as long as the universe exists, in a state that allows matter to persist. Baryonic matter. The protons, neutrons, and electrons that make up atoms is essentially stable on time scales of 10 to 40 years or longer, according to our best understanding of physics. The comet will outlast our sun, which will die in about 5 billion years. It will outlast the Milky Way's collision with Andromeda Galaxy in 4 billion years. It will exist long after every star currently shining has exhausted its fuel. There's something profound about that permanence contrasted with the ephemeral nature of our observation. We watched 3IATLAS for less than a year. It will exist for trillions of years. Our civilization, our species, our planet, all temporary. The comet, it endures. But let me bring us back to the human scale, because that's where meaning lives. In January 2026, 3IATLAS will have faded to perhaps magnitude 14 or 15, visible only to dedicated amateur astronomers with large telescopes and to professional facilities. Most people will have forgotten about it by then, if they ever knew about it at all. The news cycle moves on. Life continues. But for the astronomers who studied it, for the scientists who analyzed its spectra for the mission, planners who coordinated spacecraft observations, for the amateur observers who contributed data points for all of them, 3IATLAS will remain vivid. It will appear in papers, in conference presentations, in dissertations. Graduate students will build careers analyzing the data. The comet's chemical fingerprint will be compared to future interstellar visitors, helping to build statistical understanding of galactic comet populations. And perhaps decades from now, when we've detected dozens of interstellar objects through the Vera Rubin Observatory and other next-generation surveys, when ESA's Comet Interceptor mission has successfully rendezvoused with one of these visitors, and returned close-up images and direct samples, when we've built a robust understanding of how common different comet types are and what that tells us about planet formation across the galaxy. Perhaps then we'll look back at 3IATLAS as a pivotal moment, the third detection. The one that showed us just how extreme cometary diversity can be. The one that challenged our assumptions and forced us to think bigger. There's a beautiful symmetry to it all. The comet came from the ancient past, formed when the universe was young. It carried information across space and time, a message in a bottle thrown into the cosmic ocean billions of years ago. We found the bottle opened. It read what we could. And now the bottle drifts on, carrying its secrets onward, perhaps to be found again by someone else, somewhere else, someone else. Or perhaps not. Perhaps we were the only ones who will ever know 3IATLAS as anything other than a frozen rock in the dark. Does the comet know we observed it? Of course not. Does it care? No. It's not conscious, not alive, in any biological sense. It's ice and rock and frozen organics following the laws of physics, responding to gravity and heat and momentum. But we observed it, and we cared, and that matters. That's what consciousness does. It creates meaning where none existed. The universe doesn't care about 3IATLAS. But we do. We assigned it a designation, tracked its motion, studied its chemistry, wrote papers about it, created visualizations of its journey. We transformed a random lump of ancient ice into a scientific treasure, an educational opportunity, a source of wonder. And in doing so, we connected ourselves to the broader cosmos. Every photon of light we captured from 3IATLAS traveled 167 million miles at the speed of light, carrying information about molecular composition, surface temperature, particle sizes. Those photons entered our telescopes, struck our detectors, got converted to electrical signals, processed by computers, analyzed by software, interpreted by human minds. Through that chain of physical interactions, the comet touched us. Not literally, not physically, but informationally. We became connected to it and through it to the star system, where it formed to the galaxy we share to the universe that contains us all. This is what astronomy offers us perspective. In our daily lives, we worry about immediate concerns, work relationships, health, finances. These concerns are valid and important. But occasionally it's valuable to step back and remember that we live on a small planet orbiting an ordinary star in a galaxy containing hundreds of billions of stars, in a universe containing hundreds of billions of galaxies across a span of cosmic time measured in billions of years. We are tiny, we are temporary, and we are also extraordinary. The universe becomes conscious of itself. Matter arranged in such a way that it can study matter atoms, examining atoms, stardust, contemplating stars. 3IATLAS reminds us of our place in the cosmos, not central, not special in any cosmic sense, but participants. We're part of the story. The comet's journey through our solar system is a chapter in its billion-year history, and our observation of that passage is a chapter in humanity's story. Both chapters matter, even if they matter differently. The comet will continue, regardless of whether we exist. But the fact that we were here, that we noticed, that we studied and learned and wondered, that's our contribution to the universe. We add meaning, we add purpose. We transform blind physical processes into narrative, into knowledge, into something that can be shared and remembered and built upon. So as 3IATLAS fades from our instruments, as it returns to the darkness from which it came, what do we take away? What's the lesson here? I think it's this: the universe is more vast, more ancient, more diverse, and more wonderful than we imagine. Every time we think we understand how things work, nature surprises us. Oumuamua surprised us. 3IATLAS surprised us. The next interstellar visitor will surprise us too in a different way. That's not a failure of science, it's an invitation. It's the universe saying, you don't know everything yet. Keep looking, keep learning, there's more to discover. And there is so much more to discover. We've detected 3 interstellar objects in 8 years. 3. Out of trillions that must exist. We've sampled 1/10 trillionth of 1% of the interstellar population. Every new detection will expand our understanding. Every new chemistry, every new structure, every new trajectory will add another piece to the puzzle of how planetary systems form, how they evolve, how they populate the galaxy with their ejected debris. 3IATLAS gave us extreme chemistry, 8-to-1 CO2 domination, unprecedented in our experience. What will 4I give us? Maybe a nitrogen-rich comet from an ice giant formation zone. Maybe a methane-dominated object. Maybe something even more exotic, a carbon-rich comet from a carbon star system with silicon carbide dust and bizarre organics we've never seen. Maybe an actual intact planetary fragment, a piece of a destroyed world. The possibilities are endless because the universe has had billions of years and billions of star systems in which to explore every possible combination of chemistry, structure, and dynamics. And we get to witness it. We get to be the generation that transitions from interstellar objects are theoretical to interstellar objects are studied routinely. Our grandparents couldn't study interstellar visitors because we hadn't detected any. Our grandchildren will probably have dozens of examples to compare, maybe hundreds. We're living through the transition, the moment when these cosmic wanderers shift from mythology to statistics. That's worth reflecting on as you drift towards sleep tonight, as you let these thoughts settle in your mind. Somewhere out there right now, 3IATLAS is moving through the cold darkness between worlds, carrying the frozen chemistry of a star system that died before ours was born. It passed through our neighborhood for a brief moment, shared its secrets with us, and continued on its eternal journey. We were fortunate enough to be here, to be watching, to be curious enough to point our telescope skyward and ask, "What are you? Where did you come from? What can you teach us?" And it answered, not in words but in light, in photons carrying spectral fingerprints, in orbital deviations, revealing mass and activity and brightness variations, revealing rotation and shape. We listened, we learned, we grew wiser about the cosmos we inhabit. The story of 3IATLAS is really the story of humanity's relationship with the universe, perpetual students in an infinite classroom, always learning, always surprised, always humbled by how much we don't yet understand, and always curious enough to keep looking, keep questioning, keep reaching toward the stars that we came from and the mysteries that surround us. As 3IATLAS disappears into the cosmic distance, as its light fades below the threshold of our most sensitive instruments, as it returns to being just one of trillions of invisible travelers wandering the galaxy, we carry forward what it taught us. The data remains, the knowledge persists, the inspiration endures. And the next time a faint moving object appears in our telescopes, showing unusual velocity, showing hyperbolic trajectory, showing chemistry from another world, we'll be ready. We'll point every telescope we have at it. We'll study it from every angle. We'll learn everything we can before it too fades away. Because that's what we do. That's what makes us human. We reach out. We explore. We wonder. And occasionally the universe reaches back, sending us messengers like 3IATLAS to remind us that we're part of something much larger than ourselves, a cosmos that's ancient, diverse, dynamic, and absolutely filled with wonders we've only begun to discover. Thank you for joining me on this journey through the story of 3IATLAS, the cosmic visitor that came from another star, the ancient traveler carrying chemistry from the early universe, the messenger that briefly connected two worlds separated by incomprehensible distance and time. Whether you listened while wide awake or let these words carry you gently towards sleep, I hope you found wonder in this tale of exploration and discovery. The universe never stops surprising us. New discoveries await around every corner of space and time. And I'll be here to share those stories with you, to explore those mysteries together, to find meaning and beauty in the cosmos that surrounds us. Until we meet again under the stars, keep looking up, keep wondering, keep exploring. The next cosmic visitor might already be on its way, carrying secrets we can't yet imagine. And when it arrives, we'll be here together to witness its passage and learn what it has to teach us. Sleep well, dream of distant worlds, and know that somewhere out there, ancient travelers are making their way through the eternal night, waiting to share their stories with anyone curious enough to listen.